Yeah, sorry for, okay. Yeah, in order to better interact with the daily object made by human, so we need a human-like hand. So compared with like parallel gripper, our human-like hand is much easier to manipulate with this kind of daily object. So does this humanoid robot hand. In this industrial, there's several common use Dexterous hardware that is manufactured for years, like a bionic hand, shadow hand, a switch hand, a legal hand, DRL hand, and Vincent hand. So the advance of this hardware also motivate us to do better for the algorithm side of Dexterous manipulation. Yeah, maybe you have already seen the video of Tesla boat several months ago. Yeah, and nowadays the humanoid robots becomes a really popular topic for the robotic research community. Yeah, however, there are several unique challenges for Dexterous manipulation. The first one is a challenge for modeling. We know that all these model-based methods need a good physical model to do like maybe model predict control, trajectory optimization. So however, the rich context and complex interaction pattern will prevent us to get an accurate model for Dexterous manipulation task. Also, the high dimensional state and action space will make it more challenging for learning-based method like reinforcement learning or imitation learning. And also we know that as a robotics researcher, we always suffers from the hardware failure in our experiment. And this kind of failure is more common for Dexterous hand compared with parallel gripper. For example, if you have a tendon-based hand, like it's very, yeah, it's pretty common that you may break your hand and then you will like cannot continue your experiment. With this challenge, we also have some unique opportunities for Dexterous manipulation. The major advantage is the morphology similarity between Dexterous hand and human hand. So we can try to leverage the data from human side to learn better Dexterous manipulation policy. And also the ones of tactile sensing technology also provide us better information for Dexterous hand. And finally, you'll know that different from parallel gripper, our human-like hand can do a lot of different tasks. And in a long horizon manipulation scenarios, we can use one manipulator like the Dexterous hand to achieve a lot of different tasks, which can be changed in a long horizon. Yeah, so there is like unique advantage and unique challenge for Dexterous manipulation. So that we want to organize this learning Dexterous manipulation workshop today to talk about these challenges and opportunities here. Yeah, maybe let's Mohi, another workshop organizer, to introduce the schedule of this workshop. Yeah, welcome, Mohi. Thank you.
Hello, everybody. I'm Mahi, and I'm one of the organizers of this workshop. I am from NYU, and thank you all for being here today. I wanted to say that because this is on a Friday after a very long conference, and all of us are pretty tired and quite conferenced out. So I'll try to keep this short and move right on to our talks. But let me just introduce the schedule, like the speaker lineup that we have for today, and also the poster session that we're going to be having. So first, I want to say that like our workshop is on broad scale divided up into 3 sessions. The first session is mostly focusing on our virtual speakers. That would be Professor Pulkit Agrawal and Vikash Kumar. And then we're gonna have a little break and poster session. So we kind of wrapped it up all in the same one. We're gonna have some presentations from paper authors that we have here. And we're also gonna have like the poster presentation in the poster boards that you see behind you. And we're gonna wrap up the coffee break at the same time. So if you're having coffee, walking around, talking with the authors, that would be the time. After the poster session and coffee break at 3:45, we're gonna have 2 in-person speakers. So one of them would be Tess Hellbreakers, and another would be Abhishek Gupta. And finally, once we have had that session from 4:45 to 5:15, we're going to have 2 student speakers that we invited. And with that, we're going to be wrapping up our workshop. It's a half-day workshop, as you're probably well aware. And this is kind of more details about the poster session that we're going to be having. Large scale, this is going to be 2:45 from 2:45. But again, if you're presenting a poster there, you don't have to stay there the whole time because the coffee break is also during the same time. So feel free to walk around, ask other authors questions. And given that we are all interested in pretty much the dexterous manipulation part of things, I think you would find interesting topics to talk about. And like we're going to have 14 posters around here. So if you're attending, please feel free to ask questions. Unfortunately, there's no real virtual equivalent to this part. So if you're joining on Zoom, I'm sorry about that. And then we're going to be closing out at 5:15, 5:15 to 5:30. We're just going to be giving out a summary of the workshop, all the things that we talked about today. And like hopefully you'll have a lot of things that you're going to be going home with from this workshop. So that is all. I'm gonna close out our intro session. It's almost 1:45 and time for our first speaker. So we'll wait for that a little bit. But thank you so much for attending this workshop. If you have friends attending here who might be interested, also let them know that we are here in this room, and also we're on Zoom. So if you're, if you have lab mates somewhere else who cannot attend in person, send them the Zoom link. It's pretty easy. Like it's our website, learn.dexhand.github.io/Zoom. So they can join there as well. But yeah, thank you so much for your attendance. And once again, we're excited to have an exciting lineup of speakers. We're excited to have a lot of cool posters that we're going to be seeing, a lot of interesting student talks as well. So once again, let's give our way to Professor Pulkit Agrawal, who's going to be having our first talk. He's on the Zoom call right now, and I'm going to be stopping screen sharing so that he can take it from here. Thank you. Also, let me just give an introduction, or Yuzhe, do you want to do the introduction? Okay, so Yuzhe is going to introduce our first speaker, and we're gonna take it from here. Thank you so much, everyone.
Maybe I can introduce the first speaker, Professor Pulkit. So Professor Pulkit is assistant professor in the Department of EECS of MIT. Professor Pulkit's research interest spans robotics, deep learning, computer vision, and reinforcement learning. His work received the Best Paper Award at the Conference of Robot Learning in 2022, and the Best Student Paper Award at the Conference of Computer-Supported Collaborative Learning in 2011. He is a recipient of the Sony Faculty Research Award, Salesforce Research Award, Amazon Research Award, a Fulbright Fellowship. Before joining MIT, Professor Pulkit received his PhD from UC Berkeley and bachelor degree from IIT Kanpur, where he was awarded the Director's Gold Medal. Yeah, let's welcome Professor Pulkit for his talk towards real-world ready dexterous manipulation.
Thanks for having me, and thank you so much for the kind introduction. Is my voice audible?
Yeah, I think it works for your audio.
The audio works fine?
Yeah, the audio works well.
Okay, perfect. So should I start now?
Yeah, you can start now.
So, as we know, the theme of this workshop is about dexterous manipulation. So let's consider, the problem that many of us are interested in, which is about using tools. For a moment, let's consider, suppose we want robots to chop vegetables, right? Now, to do that, what we need to do is to have a knife in a way so that the sharp face of the knife faces the vegetable. That is the only way we're going to be able to cut vegetables. Typically, what you have is, a knife might be lying on your table, it might be on your drawer. So the first thing we need to do is to grab this knife, and then we need to reorient it before this knife becomes useful as a tool. Now, we all know that there has been a lot of, progress on the problem of grasping. But reorientation has something which has remained challenging, right? But reorientation also seems to be precursor to general tool use, right? If you want to use tools in a way that they're not attached to a robotic hand, but they're present in the environment, we're going to pick them up and use them, then there is not a way that we can bypass reorientation, right? And reorientation is happening in many things that humans are doing, all the time, sometimes out of necessity, and sometimes, just out of, right? Here are just some videos showing reorientation in the human world. Now, this remains a well-studied problem with demonstrations in 1980s, 1990s, doing demonstrations on some objects, to the more recent work from OpenAI when they were trying to reorient this Rubik's cube. And the problem is hard because it's high dimensional control, and there are discontinuities coming in from contact, making it a continuous discrete optimization problem, which is well known to be NP hard. Despite that, there has been progress on this problem, as is evidenced by these videos. But current systems have some limits. The one big limit is that they only work with few objects, and namely the objects that you're seeing on the screen, right? Which means that these systems are unable to generalize to new objects. Which, in my opinion, is a big limitation if you want to have a general system which is deployed. Right? Then the other situation is that if you look at all of these images, what you find is that the object is resting on the hand, right? Which is what I'm calling this upward, facing hand configuration. So in such a scenario, the object is supported by the hand, so it does not really need to fight gravity. But if you consider the scenario on your right, where the hand has to fight gravity, at every point in time, because if it takes a wrong action, the object is going to fall down, and it is an irrecoverable failure. Now, just for a moment, think about tools that you might be using. For example, using a screwdriver or using a knife. It's almost always in this particular configuration that we are using tools. Right. So the problem that we set out to do was to say, how can we build a reorientation system which can generalize to many, many different objects, perhaps can work with different orientations of the hand and really operate with, real world observation. Now, just to give context for what we mean by real world observation, if we do look at the system that OpenAI had, this is what they had. They had, so many cameras in this rig. And the reason for these cameras was to get good estimates, both of the object, but also of the fingers, right? While, such a system, which can give very precise state estimates is good in a lab, it's not very practical for real world deployment. So what we wanted was something which is real world ready. Now, what I mean is, we are using, commodity cameras, and there's a single camera looking at the object. And then this hand, which is, we took an open source hand and modified it, is tasked to reorient this object. Now, this is something, if it works, we can, hopefully deploy it in realistic settings or on a mobile manipulator. And then, as we discussed before, we want to be able to work on complex shapes and want to be able to generalize to new objects. So the approach we are going to be taking, which was work done by Tao Chen in my lab, is to train, policies using reinforcement learning in simulation. So, we use Eyesight Gym and have, hundreds and thousands of environments in which the hand is trying to learn reorientation. And then we're going to transfer these policies into the real world. And the general idea and the paradigm we're going to be following is that in simulation, there is a lot more information available than in the real world. For example, we can directly access object velocity, object current pose, and these things, in the real world, we need to estimate from vision, but they're really available in simulation. right? So here is a state space that we use in simulation, consisting of joint velocities, fingertip information, object information, and an object goalpost. This information goes into a new network, which is a policy pi theta, and we are training it to maximize the reward function, where reward function intuitively is high if the object is close to the goal orientation. Right? So we're going to be calling this a teacher policy that is trained in simulation, and because we use privileged information, it is easier to train. But this policy cannot be deployed because it needs access to parameters like object velocity and object current pose, which need to be estimated from visual data. So for real-world deployment, we are going to have a second policy, which takes in as input the joint positions, the goal pose of the object, and readings from the camera. And now what we're going to do is we're going to learn this policy via supervised learning, where we say that the outputs of the second policy have to match the outputs of the first action or the first policy, right? And this approach, is known as teacher-student learning. Has been used. This idea of teacher-student learning has been used by many recent works trying to do simple real learning. So, we are going to generally follow, a similar philosophy of first train with RL in simulation, then for real world deployment train from visual. And then let's see how well this visual policy actually performs. So our setup looks as following. There is a camera looking at the object in the hand. We get the point cloud observation and the joint position as input, and the output is joint commands. Here is the same setup from a side view. And what we're going to be doing is only evaluating on novel object shapes that the system was never trained on. So here is the first result. On the top right, we are seeing the goal orientation in which we want the object to go. And this is the current state of the robot. So here it can able to reorient this object close to the goal. There's another example where we don't use a 3D printed object, but a real world object, and you see the goal is specified as the point cloud of the object in the desired configuration. And in this video, what you'll see is that the hand stops at the right configuration, and then it will restart and go to the next configuration. So what we actually found is this problem of stopping and restarting is actually much harder than doing continuous reorientation, because you need to overcome inertia. Now, of course, the system is not perfect, and we are, so we can do reorientation in a way that we can generalize to new objects, but the precision can take quite some improvement, and we get within 25 degrees of the target right now on average. Right. Here is another example where once the agent is able to reorient the object to the desired configuration, the grasp is stable enough that we can move the hand, and so that once we reorient the object, we can think about starting to use it, right, or starting to use the tool if tool is the thing that we are reorienting. So what were the ingredients which were required to get to where we were able to get? The first thing was to really leverage privileged information in simulation to be able to train reinforcement learning policies in reasonable amounts of time, and then imitating them with a policy working from real world observations coming from a camera. Second were, a series of system level choices. For example, we had to speed up point cloud based training. Initially, it was taking 20 days. With some innovations, we were able to get it to 4 days, which were really critical for experimentation. Then this controller was running at 12 hertz in the real world. And to do this, we required particular architectural choices. For example, over here, we were using sparse CNNs. Then, what we found quite critical to real world transfer was identifying the parameters of the manipulator itself. For example, we have a manipulator in the simulation, we have manipulator in the real world, but what are the lag of the motors, right? And without knowing the lag and the friction, the sim to real performance was quite bad. So what we did was system identification of just the manipulated dynamics, which really helped in getting high performance. And then there were considerations about the particular reward function that we were using, and also the hardware, right? And when I say hardware, it's the arrangement of fingers, but also the fact that we used soft fingertip that we iterated over. And what we found is using soft fingertips really helped in getting better generalization, even though the whole system was trained in a rigid body simulator. So in summary, what we were able to achieve was dynamic reorientation, which works in the full SO3 space, irrespective of hand facing up or down. It can balance objects suspended in air. And all the results are really with one controller for many objects. It does generalize. And the whole setup is open source, low cost, costs less than $5,000. So if you want to replicate it and test out our policies or use the setup for other Dexterous manipulation tasks, I do think it's a good platform to consider. Now, while we were able to satisfy this desiderata, there of course are limitations. As I mentioned, one of them is the precision of reorientation is not as high as we would like it to be. And the other is, sometimes the hand, does drop objects, as you will see over here. So the next question for us was, how do we go about improving the system? And so, there is some improvements one can make on the algorithm side, but I think there are other considerations also on what kind of sensors and hardware we are using. For example, in the current hand, there was no tactile feedback, which meant that the robot really does not know if the object is slipping out of the hands. And so the next thing we considered was, well, can we incorporate tactile information to do reorientation? But we were, then running into this issue of, what is a good tactile simulator to use, right? So we had this work in Codal last year. We were trying to build a tactile simulator really for the gel site sensor, right? So what you see is, as this, rectangle is rolling on the ball, we can see the normal force and the tactile force field. And, what we can do is we can place these tactile sensors in complex geometries and still be able to simulate it. And what we showed in this paper was that we could do sim to real transfer on things like, peg in the hole. Once we have the simulator, then we started saying that, hey, could we now start real world experiments, right? So over here, you see the same hand I've shown before, but now we have these omnidirectional gel site sensors, which we took from our collaborators in Ted Wilson's lab, to ask things like, could we improve reorientation with touch? But also perhaps, look at other problems, for example, if there's a bag, can my hand go inside the bag and grab objects, right? I mean, when the hand goes inside the bag, you may not be able to see the objects, or objects are heavily occluded, so you might really be relying only on tactile sensing. So just as a way to see, how far we can get in this direction and how good really are these sensors, we set up the following system where this hand, first is given an object which it touches to develop a tactile representation of it. Right? Then, we throw other objects on the table, turn off the lights, and then the hand is tasked to find the target object. Now, this is analogous to, you waking up, perhaps in the night, and then trying to find, your phone. Right? So what you see is, this hand, goes along, trying to find, to locate different objects. Then it goes and touches these, different objects to find which one of them might match the target. And once it has touched all the objects, then it will go and try to attempt the one which it thinks is the closest to the target orientation. So we had, even though this, cup was in a different orientation, it still identifies it as a target and then goes picks it up. This was, work led by Samir, Tao, and Abhishek. So now that, we know that these sensors are, working and we can use them, with these dexterous hands, then we said, well, can we go down and try to do, tactile reorientation? Right. So first, what do I mean by tactile reorientation is, if we just have, touch sensors, then can we start reorienting objects? Right. So this is first doing experiments, with, the shadow hand speed, which has been out there for quite some time, where the red dots, are showing you the tactile readings, and the problem setup is similar. We want to go from current pose to a target pose. So now, if you want to start using tactile sensors and use the same sim-to-real approach, we do run into some issues, right? And I'm going to illustrate what this issue is. So remember, what we had is this paradigm where we have a teacher policy operating from previous state. And then in the real world, we have joint positions, the goalpost, but now instead of vision, we're going to have tactile readings, which the student has access to imitate the teacher action. So the problem is that if you just get sparse readings of touch, you may not even be able to estimate the pose of the object. And if you don't know what the pose of the object currently is, it's hard to come up with a sequence of actions to reorient the object. Right? So it may not be possible to directly copy the teacher. Now, to make this point maybe more intuitive, let me explain this with a simpler problem. Right? So consider this 2D grid world where we have this agent, right? And what we have is a setup where there are two possible goal locations. And in some episodes, there is one goal. And in the other episodes, there's a different goal. Right? So it's a stochastic environment where, some trials you have to go to blue thing and some trials you have to go to the green thing. So now assume that, the teacher or the expert, can observe the whole map. So it does know whether the goal is at the blue location or if the goal is at the green location. But now consider the student or the learner, which is trying to learn from this teacher, it cannot observe where the goal is. Right? So its observations are partial. But what it can do is it can go to the pink block. And if it goes to the pink block, it reveals where the goal might be. Right? So this agent has to go to the pink block and then it figures out where the goal is. And based on that, it can make a decision on when to go left or right. But if you see, this agent cannot mimic the teacher. It has to deviate from the teacher and go to the pink block before it can go to the goal. Right? So if you're simply, doing imitation learning, it doesn't work because the teacher has too much information. The other scenario might be that the teacher itself is suboptimal. And therefore, if you just try to imitate the teacher, one can never outperform the teacher. So the one approach that people use to overcome these issues is to say, we are not just doing imitation learning, but we are also going to add a reward. And we'll jointly optimize the reward function plus lambda times the imitation learning loss. Right? And the hope is that by this formulation, we can do better than just doing RL or just doing imitation learning. But then the key question really becomes is, how do we find this balanced lambda? And it turns out that, finding this balanced lambda is really problem dependent. For example, if we are in this scenario where the teacher is too good, for example, where we are learning from touch sensing or the example I showed before, now the agent first needs to explore to gather information, which is where it should trust its reward function more to do exploration, and then it can imitate the teacher. Versus if you are trying to learn from a suboptimal teacher, maybe you want to first follow the teacher to get a reasonable policy, and then you want to trust the reward function more. Right? So in both of these scenarios, the dynamics of lambda are going to be quite different. Right? So, what we want is a principled method to find this balance between reinforcement learning and imitation learning, instead of, having some heuristics that one has to tune, on a per problem basis, right? So the key idea that we came up was to only leverage the teacher when it is useful. Right? To illustrate the idea, suppose we have the performance of a policy pi represented by J pi, where J pi is the sum of rewards if we are collecting data from a policy pi. Right? So the idea is that we should only use the imitation learning or guidance from teacher if it helps the policy get better rewards than just training from RL alone. Right? Now, of course, we never have access to the optimal RL policy. But what we can do is we can train, two policies simultaneously. A RL only policy and a policy learning from, RL and imitation learning. So the way it looks like is, our agent is, collecting data, and with this data, we train two policies, RL plus alpha times the imitation learning and just RL. And then we compare the performance of these two policies to adjust this coefficient alpha. So what this does is it dynamically changes, how much one should trust the teacher versus the rewards in the hope of finding a better solution. And this algorithm is what we call as TGRL, or teacher-guided reinforcement learning. So in terms of comparing results on this tactile reorientation task, if we just look at the performance of reinforcement learning, which is SSC, this is the performance is on y-axis and x is number of training steps. So if you look at SSC after 16 million time steps, this is what it gets. If we consider the Oracle teacher, which has published information and just do student teacher learning, we get this, orange curve. But if we use the method that I just told you about, we can overcome and go beyond the teacher and actually achieve, better performance. Now, there are comparisons in the paper where we show that, our method works better, or the TGRL works better than many different, hyperparameters that one might, search by doing a hyperparameter search. And the reason is that, our, modulation between the teacher reward and the imitation reward is dynamic. It's changing during the training instead of it being like a fixed coefficient. So now, and this technique is something that we found to be important to get at least good performance and simulation with tactile sensing. And, we are, still waiting to see how this will, pan out in the real world. And the last thing maybe I want to touch upon is that it's not really just about tactile sensing, which is the thing that we need to improve in this manipulator, but there are hardware considerations. For example, there is no palm in this manipulator, this hand is not very compliant. And, how do we know, what is the right finger shape for doing the tasks that we are interested in? So then what we started doing was we said, hey, can we design hands, which might be optimized for a particular task or a family of tasks? But then designing hands is a slow process. So could we come up with a computational way of quickly designing hands? So what I am showing you are 4 different hands, and these blue things are gloves, which one can put on the hand. And these gloves are actually, tactile, in the sense that they have fibers which crisscross. And when the fibers are pressed, we can get tactile readings from them. So now what we can do is we can come up with any of these designs in a matter of hours to days, instead of it being, weeks to months. And the hope is that these hands can be covered completely in tactile gloves, which can, help us with, many more dexterous manipulation tasks in the future. And the way this is really working is that there's a grammar of, designs. So, based on this grammar, one can sample, different design configurations, as, you can see in this video. But then, if you sample from a grammar, you might get a design, but this design may not be fine-tuned towards your particular task. So you might still want to adjust the shape of the hand. And what we guarantee is that no matter whatever adjustment you make, in our platform, the hand is always 3D printable. Now, after you decide, where, what your shape is, then you can decide where you want to put your tactile sensors, right? So over here, we click, the user clicks and they say, okay, I want tactile sensors over here. Then we get files for 3D printing, the hand and, 3D printing the tactile sensors. And then these components are assembled and we end up, getting the hand. So, here are some examples of, this hand, trying to, cut paper. Right? So it does cut the paper, and but then if it is also tasked to cut acrylic, what it realizes is that the acrylic is too hard, and therefore it shies away and comes back and doesn't tries to cut the acrylic. Here is the hand trying to tighten a nut over here, and when it figures out the nut is tight enough, it stops the process. But this was the first iteration of this tactile sensor, which we did with Wojcik Matusic's lab. Now, while the sensor works, it was not as reliable, and as over time the sensor readings shifted. So right now we are working on better prototypes of these tactile sensors. And finally, what one can do is over here we have a grammar, but someone was manually using the platform to design hands. But you can also think of automating the design process, where instead of it being manual, we can co-optimize the hand for the tasks that we're interested in. And I'm just showing you a few examples of this co-optimization process. We can manufacture these rippers and work done in collaboration with them. So in summary, I think attacking this dexterous manipulation problem requires advances not just in control, but also in perception and hardware. And what I presented you was a full stack perspective on how we can think about making progress in dexterous manipulation. And just to end, I think when we think about dexterous manipulation, we really think about hands and manipulators. But there are fun things one can do in dexterous manipulation, which are with respect to locomotion, right? So, for example, consider this problem of trying to manipulate a soccer ball, right? In this problem, also is in some ways a dexterous manipulation problem, because one needs to balance the robot on its 3 legs and still use one of the legs to hit the ball, right? So similarly to many of the issues, that we face, in reorienting objects with the hand, I think dexterous manipulation can be studied in, many setups, which are not just with the hand, but also on, other platforms. With that, I'll end, and happy to take, any questions.
Thank you, Professor Pulkit Agrawal, for this amazing talk. We will have time for 1 or 2 questions. So if you guys have a question, please come up to the mics and we can relay your questions to Professor Pulkit Agrawal. Thank you. All right, if people don't have a question, then I can start with a question of my own for Professor Pulkit Agrawal. My first question for this would be, what are the major challenges that you have faced while trying to transfer the simulation learned policies to real world? Because as some of us have already tried out and many times have not found success in the transfer from simulation to real worlds.
Yeah, I think it's an excellent question. And I think sim to real is not a problem that we think we have solved. And I think there's still a lot to be done over here. So, the one thing that we found really key was modeling a manipulator that, it was really important, because alternatively what you would do is you would do domain randomization, and that is what would make things be conservative. So I think if you can identify the system as much as possible, then that means that you can use limited domain randomization, which helps you maintain performance and still be able to transfer. The thing that, I think still remains, quite hard in this particular setup is, figuring out when to stop. So that is, one big, failure mode. In simulation, we always know when to stop precisely. But now we're relying on readings from a depth camera, which is heavily occluded, to figure out when to stop. And, and that remains a substantial challenge.
All right, thank you. By the way, if you're on Zoom, please feel free to ask a question on the chat. We can also relay that, and also I'll read it out for the listeners in the hall. Yes, there's one question. Please go up to the mic, and please let us know if you cannot hear them on Zoom.
Yeah, first, thanks.
I think so.
Thanks for the great talk. I had a question about the hand design, like specifically the hand design project. I may have missed this, but do you guys have plans to work on how to, like, for example, predict what might be the best designs, like given task A, B, or C, like is there a way to like predict, oh, this design will work better than this design, and maybe like automatically like have a curriculum that you can generate and things like that?
Mike, could you repeat the question?
Yes, absolutely. Yes, give me a second. So I think Shikhar's question was about the hand design project, and I think the question, and correct me if I'm wrong, was about potential heuristics or learned methods that you can use to predict a certain hand, certain morphologies would act better than others given the task or goal description.
So, so I think the right metric is the reward function that you end up getting, for the particular task you care about, right? And I think there are two things, you can think, one is, should I design the whole morphology, like should I make discrete decisions on, how many fingers I should have and where the finger should be, or should I only optimize the shape, once I come up with the morphology, or should I be doing both? I feel, doing both is something one could do, but it is also computationally, much more challenging to do. So to me, seems like a good middle ground is where one can quickly iterate over different morphologies and find something which is reasonable. Maybe in that process can be more manual. And then, really fine tuning the shape of the fingers, which then just becomes a continuous optimization problem. And then doing that with a task reward is, something we can reasonably do.
All right, thank you so much for Professor Pulkit Agrawal for his amazing talk. Let's give him another round of applause.
Well, thank you for having me and thanks for listening.
Of course, thank you so much for coming to our workshop. All right, so now it's time for us to move on to our next invited speaker. Our next invited speaker is Vikash Kumar, who is an adjunct professor at CMU, and he has had an amazing line of work behind him. He finished his PhD at University of Washington with Professor Sergey Levin and Professor Imo Todorov, and his research there focused on human-level dexterity on anthropomorphic robot hands. So very relevant to what we're here talking about. And then he continued his research as a postdoctoral fellow with Professor Sergey Levin at UC Berkeley, and then he went on and did an amazing line of work at OpenAI and Google Brain, respectively, diversifying his research on low-cost scalable systems to the domain of multi-agent locomotion. And then he followed up with an amazing line of work at Meta AI on foundational models for robotics like R3M and VIP. And all along, he has been involved with the development of the Mujogo physics engine, which is pretty much used by everyone in this room, I can assume. And he has had an impressive line of awards, but I will not take up too much of his screen time. I'll just refer to Vikash. Thank you so much for being here today. Let's give him a round of applause.
All right, thanks, Mike, for the introduction. Can you confirm you guys can hear me just fine?
I think we can hear you. Thank you so much.
All right, perfect. So let's get started. I will build off from where Pulkit left. One of the key points that he made in order to make dexterous manipulation happen, it happens at the conjunction of morphology, sensing, compute, everything put together. And I thought, like, what can I share that, like, maybe my wonderful colleagues, Pulkit, and collaborators that are also speaking in this workshop might not have. So I want to put some unique perspective. So one of the things that I've realized in the study that I've recently been involved in over the past year or so is physiological manipulation has lots of insights that we are today not exploiting. For one, in order to solve the dexterous manipulation problem, often physiology or evolution has found more complicated architectures. And it seems a little bit bizarre in the sense that why would you make things harder in order to simplify? So what I'm going to do is I'm going to share like what has physiology done. It's an exercise in reducing the problem by actually augmenting the problem and making it harder. But indeed, what ends up happening is actually the problem becomes easier. Right? And the point of view I'm going to take for this talk is motor behavior is nothing but a readout of intelligence. So the more intelligent a being is, the more articulate and more impressive the motor behavior is capable of exhibiting. Daniel Volpart actually goes a level above the statement I made, and it says human brain exists for one and only one reason, and that is to produce adaptable and complex movement. Otherwise, there is no real reason to have a brain. Every other functional can be handled without the brain, right? So the whole point of this talk is that there are two facets of intelligence. One is the cognitive decision-making side of things, and we are very well aware that how impressive neural networks have been in various fields, various domains, and this is well recognized. But there is a second facet of intelligence, which is the musculoskeletal control. And this is not as a popular opinion about intelligence, that musculoskeletal control is also quite intelligent of a process. Actually, like Mark Rabert from Boston Dynamics refers to the second point as athletic intelligence. So I'm going to actually argue that humans have evolved at the facets of these two intelligence, and it's equally important to take a look at both simultaneously. So the question is, what is so special about the musculoskeletal control? One, it's an over-actuated system. That is, there are more actuators than the number of joints that the body has. Second, it's multi-articular. That means there are multiple muscles that are involved per joint. It's multi-joint system, that is a multiple joints per muscle group. And finally, it's a pull-only system. And so from a bird's eye viewpoint, you can see how complicated this whole system looks like. And if it is this complicated, the brain must be doing something smart and intelligent in order to handle all of these complications. And evolution, it would be ridiculous if evolution came up with such ridiculous architectures just to make our life harder. So there should be some simplifying assumptions that are coming out of these complications. And that's what we are going to figure out what they are. So here is a motivating example to get to the main point, that let's just say that I have to dress up, which is on the far right. And the question here is, which of the two scenarios on the left is better starting point for me in order to do that? And I'm pretty sure like everyone in the audience would agree to me, the one in the middle probably seems like a better position to get started from rather than the one in the left. Another example, if I'm trying to prepare a salad, would you rather start from scratch, or would you rather start from a salad bar where you can just pour out a bunch of things and mix them together, right? You will start from something in the middle, then something from the far right. So what is happening over here? We are basically saying that there is a large population of individuals that have taken a raw representation from the left, which is very raw, very unorganized, and build a better representation of the world. And if we act in the better represented world, then our life becomes easier, right? And this is sort of what we are ignoring, that the most of the work actually happens in taking us from the raw form to some organized space. And once we are in the organized space, then decision-making becomes much more easier and nice, right? So that's what we are going to build on. So what happens if you work on a raw space? Basically, you are overwhelmed with the choices that you are presented with. And what happens if you're working in a well-organized and well-represented space is the number of choices are very well articulated for you, and you're making like maybe some basic choices rather than like working in the full raw space. So general intuition is that the brain is in the business of making decisions, that we make decisions and that's what the brain does. And I'm going sort of against this popular notion that brain indeed is in the business of building and updating representations. That's the primary function of the brain, that it builds and updates representation and presents us in a really nice and well-curated world. And now, if you are in that world, making decisions become easier. So with that viewpoint, let me just explain how I view the whole MVP space. So on the left, you can imagine it's a standard MVP formulation, observation, next observation, goal, reward, and action. And what I'm going to do is I'm going to just put like a representation in front of each one of them, right? And this is what I'm arguing is the brain does, that it presents a representational view of the MVP for us to solve rather than the raw MVP form. And I've taken this quite far over the last few years. For example, if you just think of sensory representations, we have things like RRL, PVR, R3M, MVP, VC1, etc. If you think of representation, which is state and next state, then you have model-based RL algorithms coming in. If you think of goal representations, there are works like Zest coming in. If you think of value function representations, then we have things like VIP and Live coming in. And finally, if you think of action representations, there are a few representational work, H2R, action chunking transformer, MyoDex, and SAR coming in. So the next few slides, I'm going to mostly talk about the action representation side of things. And this representation is much more embodiment specific, while the others could be embodiment agnostic. And that's what more relevant to the topic of the workshop today. So finally, the argument here is the brain builds generalizable representations that is extended over experiences that it has gathered so far, and it leverages them while synthesizing the new behavior. And this is the key behind the generalization principle in dexterous manipulation that we have. And if you take this representational viewpoint, there are two implications that are interesting. One, that making decision becomes easier with better representation, but the more important one is that representations can be acquired out of domain. And this is the key because robotics, as we know, is a data-hungry field, and data is very, very expensive. And if you can acquire these representation out of domain, then it becomes very, very interesting all of a sudden. And by no means I'm arguing that it's going to be easy. It's actually very, very hard. And if you think of like during the child evolution process or like development process, what happens is the parents are actually quite involved in child's progress, even though the child is not as capable initially to do a lot or contribute a lot. So the parenting or like the representation building phase is a very big investment. And I'm not going to discount that. And we need to make those investments. So finally, what the results are going to be looking like is instead of going for one agent that can solve one task, I'm going to try to build an agent that can solve all the tasks that I'm representing in the screen over there. There are roughly 57 tasks represented in the screen. And this is one of the frontiers of dexterous manipulation today, I would say, is we have known of systems that can solve one task at a time, but there are rarely systems that one agent can solve so many tasks. And that probably is the goal for this particular talk. So let me start by some results first. So I'm going to start showing some of the results, and this is single agent solving all of the tasks. And I want you to notice how like the weight of the wine glass also swirling around is pretty evident in these behaviors. Finally, when you think of like stamping behavior, you can sort of see where the pressure is actually being applied on the table. Here is another much more dexterous task where the flashlight has to be shown in different directions. Here is a cyclic and rhythmic motion of shaking a jar. Here is another cyclic motion of actually brushing a tooth, and no manipulation will be final without the Stanford bunny. So here is the Stanford bunny basically being manipulated. So how did we go about getting this behavior? So on the high level, there are two ingredients that are important. One is a task agnostic formulation of the problem. And the second is a task agnostic behavioral prior. And once you mix these two things, finally interesting things happen. So let me start building in. So task agnostic formulation is very important if you're going for generalization. And this is very well known in locomotion literature, where we do what we do is we specify a trajectory that the character should be taking, and then we just ask that character to follow the trajectory. And this is a very general way of representing any manipulation behavior where the policy can actually track locomotion behavior, where the policy can track anything that you can ask for. So we are going to emulate something like this, but for manipulation. And finally, what we are going to do is we are going to build a task-agnostic behavior prior that is going to serve as a good starting point, no matter what task we are going to do. And if you combine those two, I'm going to argue that the behaviors that I showed on the previous slide is actually going to start happening. Okay, so let me start building. What's happening if you pick a task-agnostic formulation like this? You give anticipatory power to your planner, that it knows what is going to happen in the future and it prepares ahead of time. So this is very key and it is very important. And the second is generalization gets enabled because all of a sudden we are not paying specific attention to the task and you're building a very task agnostic agent and you can fluidly change the definition of the task as you go. So the argument here is that instead of going for task specific agent where you have to fine tune reward functions, you have to provide sensory inputs of different kinds or morphology of different kind, one per task, it's an actually agent-centric paradigm that you are building an agent and agent is supposed to do anything that you throw at that agent. So that's number one. And if you just take this particular view, some interesting things happen, but that's not enough. And that's what I'm trying to show you, that if we just hit the agent with this particular formulation, it starts to do interesting interaction pattern, but these interaction patterns are not yet to the level that we can call a good manipulation is happening. So you will see it starts taking control of the object, but then soon starts to lose the object, or it starts going into some weird affordances, like you will never pick up a glass, something like this. And these are the top problems that we will run into. So how do we get around this? So we know that humans are capable of something that we call object affordances. And if you think of what these affordances are, these are basically grounding to the right submanifold in the whole space of dexterous manipulation. So dexterous manipulation evolves in a very high dimensional space. And if we can somehow magically find the right subspace in which the solution exists, then you teleport the optimizer almost to a very nice region, and then you can do amazing things. So is it possible to do that? And I would argue that yes, this is what precisely the field of 3D vision has done so far, that if you give a scene, then they are very good at the moment at predicting what is the rough hand postures that should be possible in that particular scene and that particular object. Obviously, the challenge over there, according to the 3D vision community, is this is not good enough, which I agree, this is not good enough when you think of physics not being right. But hey, is it good enough to actually give you the right affordance model? The argument is yes. I think this is very good to give you the right affordance model and ground you to the right subspace. So at the end of the day, if you take those models and project it to something which I'm showing you here, which is a high dimensional musculoskeletal model, which is tendon driven and actuated using third order dynamics, you see right off the bat that these affordance models are actually very good at predicting what should happen. So this is what we leveraged. And finally, what the whole things look like is you take any object, specify the trajectory the object should be taking. So the only specification is based on object trajectory. Then you can hit it with these affordance model, and they basically predict things like, hey, what should happen with this particular object? And you get like a posture like this, and then you generate behavior. These two ingredients are very generic to any task, and there is no reward function tuning that is allowed. This is a standard reinforcement learning PPO algorithm, but it's just specified in these two unique ways. And if you do that, then finally interesting generalizable behavior starts happening, right? So this seems a bit too good to be true. But let me just first explain. We took the object trajectory, we hit it with the pre-grasp or the affordance model output, and then you run your standard PPO agent, and that's all that is going on. So there is no fancy thing that is happening. And what ends up happening is, like, if you run standard PPO, roughly on those 57 tasks, you get 37% success. And during using this new formulation, you already start getting something like 56% success. So, okay, so this new formulation is doing something interesting, but that's probably not good enough because we want one agent to be able to solve so many tasks. And obviously, this is a very hard problem. But humans are very good at doing this. So how do we exactly do this? The way we approach this problem is we continue to evolve behaviors over time. We do a lot of things together, and somehow this simultaneous learning of multiple things actually does the right thing. And this is indeed found even in our in evolution process. When you actually take the representation of the spinal cord, it actually gets more and more expressive as you grow over time. So we are going to try to emulate something like this. And how can we do that? One of the standard thing here to do is let's just try teacher-student distillation. And Pulkit talked a lot about this, and it's a very powerful paradigm. So what we are going to do is basically train individual agents and somehow distill all of these individual agents into a policy. And we are going to call this is a good skill prior or behavior prior for our agent. Let's see how that does. And then we are going to do something different a second, which is just like basically hit the agent with the multitask learning. So simultaneously present one after the other or in some shuffled order, an agent with all of these different tasks. And what the resulting policy is going to be basically my initial behavioral policy on which any new task could be trained on. And what we found is that teacher-student distillation is not very good at giving you a good initial starting point. And next slide, I'm going to tell you exactly why. On the other hand, multitask learning actually doesn't really succeed all that much into capturing good behaviors from all of them, but it actually turns out to be a very good starting point. And this puzzled us a little bit, like what is going on? So let me just like outline what the performance looks like. So the student policy, if you distill them together in a small subset of tasks, you see the student policy is not that successful in solving all the other new tasks. But the MyoDex policy actually, this new prior, I'm calling MyoDex, is actually pretty good at solving almost to the level of all of these individual experts. So this is very interesting. What exactly is going on? That if you look at the shared representations that the experts have learned between different tasks, you will find that there is not a lot of sharing going on with the priors they have learned so far. But if you look at the MyoDex policy, there is a lot of overlap in the priors they have. And this is the reason why it is behaving so nicely, because when you're simultaneously presenting all of these different tasks to the agent, they roughly know how to align different skills or representations that are required to solve multiple things at once. But student-teacher policy, this method, basically, tries to find isolated solutions that are not as generalizable when you're trying to do task transfer. So that's why the MyoDex policy ends up doing really, really well. So let's go a little bit deeper into seeing like what exactly is doing. So first, we are going to specify this is the object trajectory I want you to follow. And in zero shot, we are going to see what the trained prior that we have shown does. So you'll off the bat start seeing that the prior is very good at going and interacting with the object, right? And it takes control over the object. And after that, if you just do a few shot adaptation, basically nails the task like from the get-go. And this is what the priors are bringing. It basically brings this initial exploration collapse where you zero down on the object like very, very quickly. And that's really the reason these things work so well. And if the task is like, let's just say small lifting behaviors like this, obviously the priors are already good enough to like do things like this, right? And if you fine tune it a little bit, then it gets much more precise. So that's really the reason these kind of methods are working. And this is just like a training curve. You will see the MyoDex policy just has like a phenomenal acceleration instead of like either training from scratch or the student-teacher policy. And now with all of these combinations, now we can solve around 86% of the tasks, 57 tasks that I've shown so far. So that's one part of the puzzle. Now, the second part of the puzzle is what happens if you're solving so many tasks all at once, something that is not just external, like a behavioral prior, something internally is also happening to the agent. And that is the notion of synergy that we are all familiar with. That synergy starts to emerge when you're trying to learn multiple tasks together. So the question now becomes, can we use them to directly learn new tasks? How can we tap into this intrinsic synergy spaces of the agent? So what we are going to do is we are going to build the muscle synergy, and we are going to see that how muscle synergy can be automatically built in high-dimensional system and how we can exploit it. So the main idea is going to be that we are going to extract something which we are calling synergy weight matrix, which is the SAR, and we are going to learn physiological control as a function of some basic patterns. And when you combine those two things, then final muscle activation patterns that I've shown all the way so far is going to get recovered. So instead of learning in this blue space, we are going to work in this red space, which is SAR, and this is a much low dimensional space, and we can exploit all the niceties of this. So how does this work? So basically, we take the agent, we subject the agent to a task agnostic play period, where the agent is supposed to interact with random objects doing random things. We take the muscle activation patterns from them, and we are going to extract a synergy space. And this is nothing but the simplest thing you can do is basically ICPCA. So we are doing ICPCA over this trajectory data, and we are just normalizing this. And that simple thing is what I'm going to call synergistic action representation. And if you learn the manipulation behavior in this reduced action representation, then all of a sudden some magical thing starts to happen, which I'm going to share in the next few slides. So roughly what's going to happen is you have a pre-training period, and then you extract SAR from there, and then you're going to ask to train a lot, to solve a lot more tasks. And the two other baselines is going to be just like curriculum-based, where you just pre-train on something and fine-tune, or the end-to-end baseline as well. So these are the two next baselines we are going to compare against. All right, so the whole process basically looks like this, that any task that you're going to throw, the observation is going to come out from there. We are going to train the policy, and the policy acts in a very interesting way. That instead of using that SAR for doing dimensionality reduction, which is this N space, we are going to do something that I'm going to call dimensionality augmentation. That in addition to all those 39 dimensions that you are working on, I'm going to add more dimensions to you. So I'm actually going to make the life much more harder by increasing the dimensionality of the problem. So an N over here for the solutions I'm showing you is 20. So I'm really increasing the dimensionality of the space. And the way this works is basically this leads to two different pathways. One is the synergistic action pathways, which are these synergy spaces. And these are the spaces responsible for very fast progress. So these are task general pathways, which are synergy spaces. And whatever is not represented in this particular pathway is going to go through the top channel, which is the task specific pathways. So anything that the synergies cannot handle is going to get handled by the individual dimensions. And at the end, you just do a linear sum of them, and that is going to be your final action space, and you're going to inject it back into the whole system. So what it starts looking like is in its traditional in-hand or reorientation problem you can think of, but now you can see the acceleration that SAR provides. On the first, I'm showing the RL end-to-end, and you start seeing initial progress and it collapses. RL plus curriculum, when you hit it the same stuff with a new curriculum, it basically starts to see some acceleration, but soon collapses. But if you start using the SAR, just because of the synergistic action representations and the task pathways as well, now there is a tremendous boost in performance that you get because of this. And this not only works on that particular problem, indeed it generalizes. So the bottom, I'm showing generalization results, where orange is basically harder and harder generalization as you move towards the right. And if you see SAR has far better generalization than training from scratch or curriculum-based domain. So that is very, very powerful. The amount of acceleration that you get is immense, and it's very stark. And the message here is also the same, that what happens is the optimizers are trying, or policy is trying to use those synergistic action pathways way more than any other dimensions that we were after. All right. And that's what leads to this tremendous success. And this is basically what the whole problem or the solution looks like, that you specify the goal and basically it's able to achieve those goals. All right. And finally, it is not just applicable to just locomotion as manipulation. It actually works in locomotion as well. So if you see the first video over there, we extract SAR from this particular video. And as you can see, the policy is not good at doing anything. It can barely make one step forward. But if you extract SAR from there, and you can see acceleration after the SAR has been extracted, that it basically shoots the performance like crazy. And what I'm showing you on the right is generalization of that SAR to much more difficult terrains. Like there is stairs over there is irregular terrains over there are rolling hills over there. So it's not that it has seen this, while we extracted SAR, it has not seen any of these situations, but it generalizes quite well and provides you with all these acceleration. So it's a very general paradigm that I'll encourage you guys to all think about and using. It's very simple. And now connecting it back to robotics, we have tried it actually on any high dimensional problem space you can think of, and the acceleration is exactly what I've been showing you. So I'm going to show you two classical problem settings that we are all very familiar with, and I don't have to explain anything in this slide. We all know the gym humanoid, and you can see the acceleration that SAR has seen on the previous best performance we have seen so far. The same thing with like the in-hand rotation stuff on the OpenAI Gym Shadow Hand task as well. Finally, I'm just going to do a shameless plug that we are actually releasing a NeurIPS challenge, which is the second edition of the challenge, trying to accelerate high-dimensional control problems. And over here, this is musculoskeletal system, roughly 80-dimensional space. And we are going to do a full arm and hand manipulation as one of the track. And the second, we are actually modeling the world chase tag competition for locomotion. And this is, again, a 100-dimensional task where you have to like avoid or evade the chase. All right. So with that, let me just do a quick takeaways. I mentioned that there are two facets of intelligence, and perhaps it's very important to study them together because there are interesting cross correlations between them, and we can do quite amazing by learning lessons from one and transferring it to the other. I also argue that agent-centric view of the world is quite interesting to look into. And in this view of the world, building representation and updating representation is the key idea that brain actually tries to follow. And maybe we can also try to view the world as building representation rather than designing policies. And finally, I showed you that some results with generalizable musculoskeletal agents, which has affordances and anticipation built in, and synergistic action pathways that are key driving force behind all the generalization we have. And these lessons actually do indeed transfer to the robotic settings as well, which I showed you some examples for. And finally, I'm representing and presenting the work that is done by all the people that I've shown on this slide. With that, I'm happy to take more questions.
Thank you, Vikash, so much for this amazing talk. I think we all enjoyed it quite a lot. So if you guys have any questions right now, please line up at the mics. We have time to take a couple of questions, so please.
Hello. Thank you for the great talk. I have a bit of a question about building these sort of action representations as a result of like a task-agnostic exploration. And I think in domains like in-hand manipulation, there's a lot of sort of like constraint on the possible space of explorations. The object is always attached to your hand, so there's not a lot of like redundant explorations that you're going to do. In domains like manipulation, I think there's a lot more chance that you're going to just do random useless things. And there's a lot less probability of contact with the object. You might just like be doing things mid-air, not making any progress. In such cases, I'm wondering exactly whether or not the strategy of building these task-agnostic play type of priors from these random explorations can actually scale to those types of scenarios.
Right. I think I would not try to defend the practical real-world challenges of doing that. That actually is indeed true. Any random exploration leads to catastrophic failure generally in the real world, which has its own set of challenges to resets. But one of the points that I'm going to highlight is the task agnostic play period for all the results that I've shown was basically done on these geometric shapes like boxes and capsules. And these are enough to transfer over to real world objects. And these play periods were not necessarily any successful play periods. It was just basically hand doing motor babbling with these objects. So none of these, like I showed much more clearly in the locomotion settings, that when we extracted SAR, it wasn't actually solving anything with any of these basic primitive objects. So you can go actually very rudimentary in the objects. You can go even very rudimentary in the task that it is showing. As long as there is some activation patterns that reasonably is covering some part of the state space, the agent by itself figures out what are the interdependencies between different modalities. For example, if the fingers cannot because of self-collision, they cannot go against each other, the SAR captures those details for you, and the exploration is not going to go in those directions.
I see. Thank you.
All right, we probably have time for one more short question. If you guys have any question, please come up to the mic and we can take the question. All right, we have one more question here.
Yeah, just a quick question on the sort of the task agnostic play. Have you looked into other ways of sort of generating that data? Like what I'm thinking of is like potentially, can you imagine like looking at like sort of an imitation learning approach, like having humans trying out some things, measuring the data from that and pulling those synergies in order to do a transfer to tasks that the human was not working on?
Yeah, we haven't specifically looked into that, but my intuition probably will be that it will actually also work. The viewpoint that we took in this particular work was that we don't want to rely on extra supervision. If we can actually automatically acquire these SAR representations, then it's going to be much beneficial, because you're not actually asking for more supervision or extra demonstrations or something. And this is one of the key ways dexterous manipulation has worked so far, that we always rely on some extra supervision to curb the exploration challenges we have. And the main motivation here was, can we do something more automatic? But having said that, I actually do agree with your intuition that if you do have some kind of offline data or like interesting data available from the experts, you can potentially also extract these representations from that. The key challenge usually is that mostly the demonstrations are state-based demonstrations, but if you actually have the actions representations available, then it becomes much more easier to extract those.
Thank you.
All right, thank you, Vikash, for giving this amazing talk. Once again, let's give him a round of applause.
Thank you guys for having me.
And with that, we are ending our online session. So we are going to take a 5-minute break. If you have a poster here, please feel free to set up the poster in the back of the room. After 5 minutes, we're going to be starting a lightning talk session where students, speakers who are presenting the posters will have an opportunity to just give a short presentation on their work. So yes, and also if you have a poster, but you have not been contacted by us, please come to the front and just tell us about your poster, and then we'll schedule you up for presentation. Thank you very much. But yes, we're taking a 5-minute breaks right now.
Oh, hi. Hi, I'm Keynote. I'm presenting Tactile board feedback for closed-loop manipulation tasks. So in this work, we study multimodal long horizon manipulation, where a robot has to switch between different contact modes to perform a tight tolerance insertion task. More specifically, we consider a situation where a robot first pivots the peg using a model-based motion planner, and then grasping it relying on a vision sensor. And after grasping, the robot estimates the pose of the peg using 2 tactile sensors attached to both fingers of the gripper, and corrects the pose using the estimation, and finally insert the peg into a hole whose tolerance is 0.5 millimeter. So these movies show the vertical insertion of the 3 different sized pegs, only relying on vision, meaning the pose of the peg is obtained by the every tag. So however, the precision of the every tag is around 3 millimeter in average, so the robot fails in completing the insertion into the tight tolerant holes. So we will solve this problem by closing the loop using the vision-based tactile sensors. So these movies show the results of the proposed method, which combines the vision and tactile images. So by using tactile images, we can compensate for the wrong pose estimations from the visions, and the robot can successfully insert the pegs into the holes. And next, we tested the vision-only policies with disturbance by human hands. The human disturbance makes error in orientation as well as translations, so the insertion becomes harder to complete, and you can see the vision-only policy fails in inserting the peg. And again, with combining vision and tactile, the robot gets more accurate pose of the object, even in orientations, so successfully complete the task. However, sometimes the wrong estimation in orientation can cause a bigger error, especially for larger pegs, so resulting in failure insertion as seen in the bottom video. So to further improve the insertion accuracy, we do regrasping after estimating the pose of the peg. In this video, the robot places the peg onto a flat surface after adding disturbance using a stiffness controller, and then successfully inserts it because there will be a smaller pose error in peg angle. So the message in this paper is that it will be very difficult to complete a tight peg insertion task just from open loop planner, and the external vision and open loop planner and external vision input, and the tactile sensors would be very useful to close the loop. Please come check our poster for more details. Thank you for listening.
Okay. Hi, I'm Siddhant and I'll be presenting our work on fast imitation. In this work, we provide a robot with a single minute of expert demonstration and propose our method, fast imitation of skills from humans of fish, which generalizes to different object configurations and types with minimal online learning. We evaluate the versatility of our approach by running it on a variety of tasks across different robot morphologies and different action spaces. Let's look at what goes wrong with doing offline imitation on small data sets. Consider the task of flipping a bagel. We collect a single minute of expert demonstration and do offline imitation on these demonstrations. As you can see, doing offline imitation in this low data regime results in suffers on different object configurations. And of course, since it fails on this simpler task, when you introduce new unseen objects in the scenario, it performs even worse than before. So as a solution to this problem, we propose combining offline pre-training with online correction. So since we want to deal with high-dimensional visual inputs, we start by using behavior cloning to learn task-specific representations. So given a single minute of expert demonstration, we use an encoder to encode observations into an encoded representation, which is passed through a policy to give us an action. In this low data regime, we observe that these actions are not these actions are not precise enough for the task that we want to perform. So in the first phase of learning, of our method, we, instead of using the policy, we use the encoder from the BC policy to obtain a retrieval-based non-parametric base policy, which given an observation gives us a base action. In the second phase, we learn corrective residuals on top of these base actions to give us a final output, action output. Thus, given an expert and agent trajectory, we use an encoder to obtain a trajectory of encodings. We use optimal transport-based trajectory matching to find a similarity score between these trajectories, and the similarity score is used as a reward to learn a residual policy using reinforcement learning. It must be noted that the OT rewards used in this scenario are only used to learn the residual policy and while keeping the base policy unchanged. So to put it all together, we start by collecting a minute of demonstrations. We do representation learning using behavior cloning on these demonstrations. We use the encoder from the BC policy to obtain a non-parametric base policy and learn residual offsets on top of these base policy using inverse RL. So let's go back to the task of flipping a bagel. We observe that fish succeeds in generalizing to different object configurations, achieving 90% success with less than 20 minutes of online learning. We evaluate fish on a variety of robot morphologies, the Allegro hand, which is a robot hand, the Hello Stretch, which is a mobile robot, and the X arm, which is a robot arm. And on average, we observe a 3.8 times better performance as compared to our strongest baseline. Interestingly, fish also generalizes to different new objects unseen in the expert demonstrations. For instance, consider this task of picking up a dollar bill. Given this demonstration, fish generalizes to different types of bills and different colored cards. However, for large variations such as a thick wallet, fish fails at completing the task. A similar observation is made in case of a bagel, where given a demonstration on a specific type of bagel, fish generalizes to different types of bread. However, it fails on the tortilla, which is soft, and renders the strategy shown in demonstration ineffective. So this inability of fish to generalize to environment variations which are pretty large is a limitation of our approach. So this is our method, fish. Fish requires just a single minute of expert demonstration and needs less than 20 minutes of online learning. It learns from images, and the video and open source code are available at the given website. Thank you.
Hello, my name is Yuzhe from Seoul National University. I am glad to present our work, Robust and Accurate System for Hand-Post Data Acquisition of Dexterous Manipulation. The motivation of our work is as follows. Data acquisition for imitation learning is a very efficient way to tackle a manipulation problem. However, human demonstration data is very hard to acquire. There are 4 methods that exist that can acquire human demonstration data that has limitations. Vision-based methods are susceptible for visual occlusion. IMU-based are suffering from electromagnetic interference and drifting. Soft sensor-based cannot distinguish deformation whether it is due to contact or movement. And lastly, exoskeletal-based, by its bulky design and large friction, it can hinder dexterous manipulation. The contribution of our system is as follows. We built a hand tracking system with visual inertial skeletal tracking system, in short VIST. This system is robust against occlusion, electromagnetic interference, and contact, and still enables fully dexterous manipulation. To shortly introduce our method fuses both visual and inertial sensor data in a tightly coupled manner. Our system VIST consists of 14 IMUs, which gives inertial data, and 4 color 65 numbers of markers, which gives image data. And the inertial data will aid visual data to Let me proceed. So the visual data will correct the IMU drifting problem, and the IMU data will aid visual data to correspond search the blob matching. So we can track all 16 segments of the skeletal, all of the position and orientation data is available. So we selected three challenging and meaningful tasks in manipulation. The first task is reorienting an HMD, the head-mounted display. As you can see, the video should start. Yeah, the video is not starting. These are actually no, it is. So maybe I can just. Sorry, the video should start, but we have some issues. I actually have the videos in my tablet, so if you're interested, you can always enjoy the poster session. So the first task involves high occlusion and magnetic interference, which can be hard for IMU-based and vision-based systems, but our system can robustly tackle this task. And we also tried to acquire data using Vicon, which is a mocap based motion tracking system. But as you can see in the plot below, the Vicon frequently loses track of the marker due to the occlusion, while our system shows robust performance. And the second task is spinning a pen, which have fast changing and multiple contexts. This task is very challenging for both soft sensor based and exoskeletal based, especially in the soft sensor based because they generally place their sensor in the dorsal side. Whenever the contact is on the dorsal side of the finger, they cannot distinguish whether the data is due to the contact or movement of the fingers. Lastly, the last task is rolling a ball while the palm is facing down. Notice the ball is not touching the floor. This is a very meaningful task because such kind of manipulation is very challenging in robotics. However, our system were also able to successfully acquire robust data. So in conclusion, we built an efficient data acquisition system, which is robust in occlusion, drifting, and contact. And we verified our system with 3 example tasks and showed potential implementation. Also, contact forces during the task can also be obtained by integrating tactile sensors or physics simulation, which we consider as a future work. Thank you for listening.
Hello guys, thanks for the waiting. So today I'm gonna talk about our actually today get accepted paper, ICCV paper, improving Dexterous grasping policy via geometric aware curriculum and the iterative generalist specialist learning. We are from Peking University and Wang. The task we're gonna focus on is Dexterous grasping, and we want to learn a policy that is universally applied to all the objects from different categories and from visual signals. However, directly learning a vision-based policy that can generalize to all kinds of different objects can be very challenging. And so that's why we propose, this is something we have learned from the previous work. We first want to learn a state-based policy, and then we want to distill to a vision-based policy. Yeah. So the thing that we did differently is that we want to handle the diverse task learning through partitioning the task space into a lot of small clusters, and then use specialists to train on each cluster to specialize and handle their task learning well, and then try to distill back to a generalist and do this process iteratively. So let's overview our method. So the main pipeline of our method is first to learn a state-based policy and then distill to a vision-based policy as what I just described. And so for the state-based policy, so we're gonna solve the problem how to divide the task space into a lot of small clusters and learn a specialist for each cluster. So the way we do it is that we want to find a feature space to embed the visual input and cluster the tasks according to their distance in feature space. So to do that, we train a autoencoder on point cloud so that this autoencoder is aware of the object geometry and also its pose. So basically, different objects have similar shape and a similar pose will be clustered into the same small cluster. And so at the very first step, we have a lot of specialists and we have a hierarchical way to distill them and to start more and more generalists. At the end, they will distill to one generalist. And this is what we call geo curriculum. And so the intuition is that each specialist just need to handle start with very small variations, and during the distillation, more and more generalists can handle better and better, like cover larger and larger variations. And this is a visualization of our geoclustering. This is the object with different pose, and so each box select one small cluster there with like similar shape and pose. So compared to category level clustering, we find that our state-based clustering actually are aware both of the shape and the pose. And actually, we can have the same thing when we move to vision-based student. They can still use dynamically trained vision backbone to perform clustering. And at that time, this vision backbone would be further aware of grasping poses. So this is what we call geometry-aware iterative generalist-specialist learning. So basically, like all the specialists will be initialized via a generalist, and then they will further learn on their new clusters. At the end of the learning, they will distill back to like generalist SGI+1, and we can do this several times. Okay. So after our state-based policy learn very well, we will distill them to vision-based generalist. And this vision-based generalist can undergo this generalist-specialist iterative learning again. And now the cluster are based on like ongoing fine-tuned vision backbone, no longer a pre-trained point cloud autoencoder. So this is like at the end of this process, we get the best generalist we can have. And so this is a vision generalist which can perform dexterous grasping on more than 5,000 objects with arbitrary pose on a table. And this is a policy, can work across all different kind of situations. So this is a diagram showing how the specialist generalist, the performance change. From the very beginning, we have a 0 success rate specialist generalist, and at the average specialist, like generalist can get 82.7 and goes to 86.8. We can see specialist is better than generalist, but it's kind of climb up. And after it's distilled to vision generalist, it goes down and it goes up again. So I will skip the numbers. So we have additional experiments in meta world showing that this specially generalist iterative learning can benefit other generalizable reinforcement learning tasks. And some qualitative results. So 5,000 different objects, our grasping success rate reaching 80-ish. Okay, and yeah, I will skip those. And we also tried on a Lego hand because the shadow hand in our lab broke. So we have to try a Lego hand. And it also worked to some degree, although we haven't aligned the sim to real very well. And why we choose, at the end, I want to emphasize why we choose grasping is just because this is the most simple thing we can try on Dexter's hand. We hope this framework can also work on all the other Dexter's manipulation tasks. Thank you, guys.
Perfect. Hi guys, I'll be presenting on some of the robot hand hardware we've been working on in the lab. I'm in Professor Deepak Pathak's lab at Carnegie Mellon from Kenny. So in robotics research, it's common to study human hands in video or robot hands in simulation. However, real-world results are often limited to two-finger grippers. Why is this the case? We find that the two commonly most used robot hands, Allegro hand and Shadow hand, are not that suitable for machine learning research. Allegro hand has weak motors that often break, and it costs over $15,000. The Shadow hand, while it is very anthropomorphic, costs over $100,000. So we're presenting two hands, and this is the first one, Leap Hand, an open source robot hand designed for machine learning. It's dexterous. With a novel kinematic structure, it can complete a variety of tasks successfully. It is low cost, under $2,000, and can be assembled in 3 hours. It's strong and durable, and it can withstand the wear and tear of machine learning research. First, let's look at its kinematic structure. To maximize dexterity, we introduce a universal adduction-adduction mechanism. As you can see on the left, Leap Hand can move its fingers side to side in both the up and down configuration. Most conventional hands, as in the middle, can only move its fingers left to right in the down configuration. When the finger is up, it just twists in place. And as you can see on the right, Allegro hand can move its fingers left to right in the up configuration, but in the down configuration, it just twists. This trade-off is good for grasping, but it's not as anthropomorphic. To make our robot hand good for machine learning, we also want it to be low cost and durable. We use as many off-the-shelf motors and brackets as possible that can withstand the wears and tears in machine learning. We use some 3D printed parts for the palm and a few brackets. Our parts list is simple and under $2,000, and you need only 3 simple tools, screwdriver and a couple hex wrenches. We'll release our assembly instructions on our website as soon as we're back from Korea. It takes a few hours to assemble it, and it does take 24 hours on a 3D printer, but you can run that overnight or autonomously. Should be simple for anyone to assemble. We'll get some applications of this hand. So first we look at machine learning, a teleoperation from human video. Here there's an RGB only camera watching my hand, and this is built on robotic telekinesis work from last year's RSS. And basically we're controlling the arm and hand. We see that Leap Hand outperforms Allegro hand in most of these tasks. This is because of its stronger and also has a better anthropomorphic structure. Next, looking at learning from human behavior, we pre-trained priors from internet videos on Epic Kitchens. These are people using their hands in videos. And then we fine-tuned with a few real-world demonstrations. We see that Leap Hand outperforms Allegro in most of these tests. That's because Leap Hand has more accurate motors. It's also stronger. Finally, we look at in-hand manipulation. You see on the left, we import the URDF of Leap Hand into Isaac Gym. We train RL policies for in-hand manipulation. And then you see on the right, we do this in the real world. We'll actually have that demo working here today. This means that the URDF is faithful to the real robot hand, and you can use it for training sim policies and then transferring to the real world. The second hand that it's still in submission, but we'll share it here, is Dash Hand, a framework for designing anthropomorphic soft hands through interaction. So in this paper, we're looking at how can we make a robot hand smaller, and how can we build in compliance? So like, because it's soft, we're able to do a lot of different tasks that we wouldn't be able to do with a big hard hand. And then how can we train the key properties that we want for machine learning? So easy to build. This can be built in around 1 day. It's inexpensive, under $2,000, and it's still relatively easy to control. It has high degree of freedom, and it's still 16 degrees of freedom, like the other hand. Looking at it, if you see on the bottom right, there's 3 tendons that go through it. Those tendons basically pull on different parts of the soft hand, and that finger is one 3D printed piece. Basically, what we do in this paper is we design iterate through teleoperation. So we use that teleoperated VR glove, which we'll have on demo here, and we improve the soft hand's performance through multiple versions. Because it's so easy to build and 3D print, we're able to build 5 different versions and show iterative improvement throughout testing. So there's automatic calibration and tensioning that makes this easy for machine learning. Controlling soft hands is like notoriously hard, but we do 2 things. One, retensioning. Basically, we pull on the tendons a certain amount to figure out the open and a closed position to the finger. The second part is calibration. Basically, what we want to do here is figure out joint angles in the finger and map those to angles in the motors. And we do that through an AR tag system. We have the AR tags on here, but then at test time, we take the AR tags off. We show a bunch of results here. Sorry, the frame rate's bad through Zoom. But here, we're using a teleoperated VR glove. And then we're also controlling the arm and the hand this way. You can see tasks like pouring, these stacking cups, picking grapes, the M&M on the bottom left, picking up cards, and then also a drill. So soft hand's still strong enough to be able to pick up a drill. We can also do more delicate things like M&Ms and grapes. We also, we're presenting this work paper here today. We do real world learning here with the soft hand. We use internet videos to create an affordance map and figure out where to grasp on objects. Then we do some real world iterative fine tuning to fine tune our policies. We're able to do a variety of tasks here autonomously with our soft hand. Because the soft hand is so soft, we're able to do this real world learning without damaging the environment. And the soft hand does not break throughout this whole process. You see picking up grapes, bagel flipping and pouring. So presented two hands here, leap and dash. If you're looking, leap is going to be released this week. It's very strong and anthropomorphic, and it's very easy to build. The URDS simulation is easy to use, and you can just get started very quickly. Dash hand, while it is smaller, and has a flexible kinematic structure. It has a smaller human-like size. It is durable for real-world learning because it doesn't damage the environment as much, and you can build in under a day. Though it is difficult, more difficult to build, and it is more difficult to simulate. That's it. Thank you.
What are those doing there? She'll show this. Okay. Will that go away? Yes, it will go away. Perfect. All right. Keep this 3 to 5 minutes as asked. Hello, everybody. My name is Ethan Gordon. I'm at the PhD student at the University of Washington, but this work was done while I was an intern at the Honda Research Institute with my supervisor, Rana Soltari-Zarin, online augmentation of learned graph sequence policies. So, motivation of this work, as for a lot of the works here, is in-hand tool manipulation. Oh, a little closer, okay. The motivation of this work, as of many other works, is in-hand tool manipulation, with the idea that in-hand tool manipulation, the sort of acts of picking up a tool, moving a tool, using a tool, you need different grasps for each one. And so that's what demonstrates the necessity of in-hand manipulation. So in this particular work, we started with the same high-level grasp problem description that all of you are working on, where you have input of the current tool pose, and this work was done in simulation at this point, so we are assuming access to a lot of this information that is privileged information, and the output is joint torques. What sort of the main systems contribution here is the addition of this contact controller. So in our lab, in the lab at Honda, we sort of designed a contact controller that could handle local grasp changes, removing a finger, adding a finger, sliding a finger. And the idea here is to reduce this sort of very large problem of in-hand manipulation to a more limited problem of grasp sequence planning, with the idea being to try to develop a low data system for actually getting this, this system to be in deployment without collecting a ton of in-hand manipulation data. So a grasp sequence planner, just choosing which grasps to use as the set point of this local contact controller. You can turn it into a standard MDP, you could throw RL at the problem, but sort of again, with this eye on data efficiency, the issue that was being run into at Honda was that there was a very severe trade-off in how much data was able to be collected. You need to collect a lot of data in order to build a very wide training distribution to handle disturbances, even in the simulation. Disturbances in the type of object being used, in the geometry of the object, the friction coefficient of the object. So the sort of main contribution of this work is that since we have designed this contact controller and we know the dynamics of that controller pretty well, we can use those dynamics at test time, parameterized by the test time dynamics of the system, to sort of take whatever policy we learned offline, whatever RL policy we learned offline, and improve it online without any additional training steps. You can think of this as a sort of one-step policy improvement that can happen online to handle changes to the environment. And as an upshot, because we sort of have this, we use the surrogate model, it's a way to sort of incorporate expert data, expert knowledge into this RL policy online. Because we have the surrogate model that we've developed, we can also use it to hot start our training procedure for faster training. So just going straight forward to the evaluation, how does this look like compared to a baseline policy? I'm going to kind of skip past some of the descriptions, the evaluation. You can check out my poster in the back for more information on that. But the key idea here is that we can sort of, from even a mediocre baseline RL policy that's doing this in-hand manipulation, we give it a new environment outside of its training distribution, it performs pretty poorly. If we do a sort of full optimization procedure, using our surrogate model with that test time environment, we get what we'll call optimal performance, and we can get pretty close to it doing this sort of 1 or 2 step look ahead procedure. So as an example, this is a case where we've now perturbed the sort of trajectory that we want this wrench to take to be outside of RL's training distribution. So if we, if we just do sort of a naive trajectory that was optimized on the training time parameters, which is on the right, we perturb the wrench down so it'll collide with the ground. Whereas RL, it runs into this perturbation, in the face of this perturbation, it is not able to adapt at test time because that perturbation was outside of its training distribution. With the idea being that if we just add this 1 or 2 step tree search look ahead, is that we can sort of recover what we would have been able to do if we had added it to added this perturbation to the RL training distribution in the first place. So we cover what we call the optimal policy here. And in this particular case, by the way, that the specific tool is using a wrench to tighten a nut, which we simulate in this case by applying a force to the tip of the wrench after the pickup trajectory is complete. Right, so these is kind of the key takeaways here. RL does well with interpolation within its training support, but when we talk about perturbations at test time, you kind of have this trade-off in terms of how much data you need to collect in order to broaden your training support. But we can actually use these kind of dynamic programming techniques, these look-ahead techniques, to add and our knowledge of both the dynamics of the problem and the dynamics of our contact controller to add that. Without retraining, allow our RL to adapt online to these perturbations. So for more information, our poster's in the back there, and yeah, have a good rest of the workshop.
All right, and with that, we have finished our spotlight presentations. We will take 10 minutes now. I know it is 3:45, and now we're supposed to start our next session, but we're going to push everything back by 10 minutes. Please take a break, drink some water, walk around. And also, the posters are in the back, so if you want to talk to the authors, please feel free to do that. We're going to be meeting back here at 3:45. 3:55. Thank you so much.
All right. Cool. Hi, everyone. My name is Abhishek. This is a bit of a strange talk. So it's not going to have any equations. It's not going to have amazing results. It's going to mostly be a bunch of reflection on how we built robotic systems for real-world RL. And I'm going to tell you how we cheated. And then I'm going to tell you how we tried to not cheat, and then we cheated again. And this is going to go over and over and over. And so hopefully, what I'm hoping you guys will take away from it is what it takes to get reinforcement learning systems to work directly in the real world, and kind of a process of system design. Okay, so I'm going to start with a bit of history, right? So this was when I started my PhD back in 2015. That's when John Schulman was doing simulated character control, and that was pretty amazing. The Atari game stuff was coming out, and then there was also AlphaGo, which is kind of a big thing back then. And so young me was convinced that RL is the is the solution that's going to solve all of our robotics problems. And so we just need to develop more sample efficient algorithms. And if we just take DQN and throw it at robotics problems, we're just going to solve everything. Right? And so that was in 2015. And then now, what is that? 8 years later, we've gotten some robotic stuff to work. But my perspective here is that, yeah, RL kind of works sometimes, but actually getting it to work requires getting rid of a ton of dirty laundry. So what I mean by dirty laundry is that a lot of the videos that you see have a ton of instrumentation behind it, a lot going on behind the scenes, a lot of cherry picking. And so a lot of people who write RL papers don't really declare their dirty laundry. And so I thought it'd be fun to make a talk purely about dirty laundry. And so what I mean by that is like, take a look behind each of these videos, try to see where we're cheating and what we can do to kind of do less of that. Right? And so since this is a paper about robotic science and systems, this is going to be mostly a systems talk about the algorithms that we needed to develop to build these systems. Okay, does the premise kind of make sense? Cool. All right, so there's lots of ways to approach dexterity, right? And so a lot of the speakers earlier today talked about things that do the model-based approach, or things that are kind of like the model-based approach. So things that do classic control or sim to real transfer. Right. So lots of speakers today talked about the more model-based approach to dexterity, which is you get a great simulator. You try to do, if you're Rust Edric, you do classic control and trajectory optimization. If you're Pulkit, you do a bunch of sim to rail transfer. And I think those can be really promising ways to do control for these kinds of hands. But today I'm going to take a different approach, which is a more data-driven approach to control. And so I want to collect data directly in the real world and see how we can use that in order to control these hands. So the hope is that by doing so, you kind of reduce the cost of modeling. You don't have to model every new object you're dealing with. You don't have to model every new environment you're dealing with, right? You can hopefully drop your robots into new environments, leave them running for a while, and have them learn new skills. And so we're going to kind of focus on this data-driven approach to reinforcement learning, where we drop them into the environment and just kind of run them and hope that they learn skills. Okay, so the approach we're going to think about today is that of real-world RL, which is no simulator pre-training. We're just going to try and do RL directly in the real world. And why is this a good idea? Right? It seems kind of wild. Well, it might be a good idea because it doesn't require any pre-provided model of the world. You can just drop things into an environment and hopefully kind of avoid modeling everything. And that in principle makes it easy to acquire new skills in new environments. And what that allows us to do in principle is to allow improving our behaviors at test time. Right? So you have an agent that's pretty good, you have a new object, you drop it in there, and in principle, it should keep getting better. Right? But what makes this difficult is the fact that I said in principle 5 times. Right? The fact that all of these things are nice in principle, but hard to realize in practice makes this paradigm not necessarily that appealing. And so today I'm going to talk about some of the dirty laundry behind the scenes that makes this hard to do. And I'll walk through a series of papers that we did to try and kind of resolve these problems. Okay. So the initial attempt that we tried back in 2019 was trying to do on-policy model-free RL, right? So we were trying to do a version of PPO or TRPO, natural policy gain was what we were using. But we were trying to use it directly on this 3-fingered robotic hand to try and do tasks where you had to do rotation of this valve object or try to flip objects on an axle, right? And so you can see that this kind of learns how to do things, right? In some cases, it takes like 10 hours, and some cases like 6 to 8 hours. And so the nice part about this is that you don't really require any modeling. It's the same algorithm thrown across all of the different manipulators. We didn't change any hyperparameters, right? And there was like no supervision needed. You kind of tend to drop the robot into these environments, and you just leave it running for a while and come back and has reasonable policies, right? So this seems amazing. Right? It's like, this is the promise of reinforcement learning. You can drop it into environments and it should learn. The problem is that, a lot of this is hiding a lot of what's going on behind the scenes. Right? So if you look a little bit behind the scenes, you'll notice that, for instance, the valve is mounted on a servo motor, and the servo motor performs resets all the time. Right? So every episode is performing a reset, and the servo motor is tracking where the agent is all the time. Right? So you don't actually need any vision. You're tracking everything by instrumenting the world. Right? And same with the axle, you can see it's on a servo motor, it resets every time you're running things. And so in a lot of ways, the environment is super controlled. Right? Some of the issues here are that, firstly, you require easy state estimation. So you have the servo motor, which is tracking where everything is. You don't have any vision. As a result, the set of tasks you can do are pretty restricted. Right? You're only doing these valve rotation tasks, things that can easily be reset and easily be tracked. You're hand designing reward functions. So I sat and wrote a bunch of hand designed reward functions, which is quite hard to do and painful. We needed this instrumentation to provide resets to the system, right? So it's constantly providing resets, and you can only do this for some small set of problems, unless you're very clever with them. And it still takes a large amount of sample complexity, right? So for just these simple tasks, if it's taking 15 hours for things that are way harder, it's not going to scale very well, right? It's not trying to generalize or anything. It's one environment, just overfitting. And so what I'm going to try and talk about today is how do we kind of resolve some of these challenges, or at least how do we start to try and resolve them? And so the first set of things we're going to try and do by learning directly from visual input and trying to infer rewards from visual input. We're going to design techniques for reset-free RL. So we're going to have things that we can run without requiring these instrumented resets, have agents reset themselves. And then we're going to try and think of how to learn from prior data to make these systems get more efficient over time. Okay, so that's going to be the structure of my talk. I'm going to start by talking about how we can learn reset-free in the real world. We're then going to think about how to remove the requirements for state estimation and instrumentation for inferring rewards. And lastly, we're going to try and make these systems more efficient with prior experience. Okay, does anyone have any thoughts, concerns, questions? Good? Okay. How much time have I used? 15 more minutes? 20 minutes? Okay, good. Cool. So the reset problem in RL is not one that people talk about a lot, right? And so what is the reset problem in RL? It's typically that most reinforcement learning algorithms assume things are episodic, right? And so when I say that things are episodic, you have some experience for a while, and then you try to reset the system back to the same state, right? So for instance, right here, you can see that Yevgen is trying to reset this puck back to the same place after episodes, after every episode, he's coming back and resetting it. And poor Yevgen gets in a lot of trouble for doing this. I show this in every talk. But this is a reality of most reinforcement learning experiments in the real world. You're constantly either instrumenting the world to do these resets, or you have, hardworking grad students who are doing the resets. And this becomes this would be fine if it's running for a couple of hours, but if you're doing this for 500 hours, you can't really use 500 man hours to do this. Right? And so we need to think about techniques that are more scalable in terms of taking the human out of the loop in a sense, and not having systems that are constantly babysat. Right? And so what we want to do is we want to build systems that learn autonomously. Right? So typically, a human is resetting the system like we have here. Right? So humans are providing the episodic resets. But since we're in an embodied system, the hope is that we can have systems that reset themselves. Right? So we try something, and then the system resets itself so it can try again. Right? And then the whole thing fits into the framework of RL. And so the first question we're going to ask is, how do we design these RL systems that can operate without interruption? Right, so as you saw in Yevgen's experiment, he's interrupting the system every 20 seconds or every 30 seconds, right? We want to see how we can have systems that run without interruption for 60 hours, 70 hours, right? And so that's the first thing we're going to talk about. Cool. And how are we going to do this? We're going to, take a very simple insight that, single task RL might be hard to perform resets for, because, you tried something, and then you're stuck. But if you're trying to do multiple different tasks in an environment, multiple different tasks can provide resets for each other. And so let's say you're in a kitchen environment, for instance, you're trying to put the kettle into the sink, you drop the kettle because you're not perfect. If you're also learning the tasks of picking up the kettle, opening the fridge, picking up an object off the floor, just by learning a different task in sequence, you can automatically provide a reset for your system, right? So the hope is that by changing not that much, just by saying we're going to go from single task to multitask RL with a little bit of clever sequencing, we're going to get systems that can reset themselves. Right? So the example would be, you'll have a graph like this. You try to perform a task. Let's say move the kettle to the sink. You drop it. Then you try to pick up the kettle, put it onto the cabinet. Maybe it's flipped over. Then you have the task of flipping it back up and so on. Right? So just by learning multiple different tasks together, the hope is that we can build these autonomous systems. Okay, we kind of buy that? Yes, maybe? Okay, so the example that we were trying it on was this 16-degree of freedom hand that we built at Berkeley, where it's trying to do in-hand rotation of this three-pronged object, right? So it's trying to reorient it to a particular position, and it has to do so by just training in the real world. Right? Now, the trouble is that when you try to do this, you'll drop the object in like 20 seconds, and then you're stuck forever. And so what we're going to try and do is we're going to try and do multiple different tasks, like recentering the object, picking it up, flipping it over, and in-hand reorientation together. Right? So we're going to learn all of them together so that we can finally learn the skill of in-hand reorientation without requiring all of this human intervention. Okay, so what does that kind of look like in practice? Well, you might have a system which tries to lift up the object, drops the object, let's say. Then you try to learn the skill of recentering. Once you've got the recentering perfect, you can lift it again. Let's say it was successful. Then you can try flipping it over, try in-hand reorientation, and so on. Right? So you have this continual process of trying different tasks, which looks something like this. Now, when you try to visualize what this looks like in terms of actual training videos, it looks something like this, right? You can these videos tend to crash. You can just leave the robot running for 50 to 60 hours. At the start, it's just learning how to recenter the object in the middle of the arena, and after a while, it learns how to pick it up. So after 30 hours, it's learning to pick it up, and after it's learned to pick it up, then you can learn to flip it over, and then finally learn in-hand reorientation. Right? So the whole point is that if you notice, there's no human really in there. You're just leaving it running, and it kind of learns behavior on its own. So it's cheap in terms of human time. And so the final behavior you learn kind of looks sensible. You're able to pick up objects, reorient them. All of this from real world data, no modeling required. So you should be able to switch out the object and get it to do reasonable things. Okay, this also works on another task, so I'll skip that for now. All right, so the question is, where's the dirty laundry, right? Obviously, this requires a bunch of cheating and bunch of cherry picking to get it to work. So let's try and think about what all of those were, right? So the first thing is we talked about this multitask setup. We said we're going to switch different tasks. Well, I wrote the switching mechanism by hand, right? So it's like a hand-designed task switching mechanism. The second is if you look at the object, there's motion capture markers all over the object, right? So you have a motion capture system, which is like getting the state of the object all the time, making it expensive. Then you have hand-designed reward functions, which someone wrote by hand, very expensive to design, and you have to do it for each of the different tasks. And lastly, this requires a huge amount of time. So this object broke like 5 times in the process of learning this. Right? And so it's a very cherry-picked object. And so we want to kind of get rid of some of these challenges. Okay, so that was the first part of my talk on reset free RL. Any questions, thoughts? No. Okay, so the first thing we thought about is, okay, we got rid of the reset problem, but we have all of this, these challenges of hand design for state estimation, reward specification, and so on. How do we get rid of the challenges of, let's say, state estimation, right? So in our system, we saw that we needed this object to be instrumented perfectly. Why do we need that? Well, one is because low dimensional state is faster to learn for, but I think the more interesting requirement for this state estimation is to do reward specification, right? So if you know the state of the object, it's easier to do reward specification as opposed to if you didn't have the whole thing instrumented. And so we had everything estimated, and then we went and wrote this complicated reward function, right? And this is relatively short for a reward function, but in general, you can get longer and longer and longer reward functions. And so we took a bunch of time to write this, but we did this for one object. You change the object, it's going to be the same amount of effort, right? So in terms of grad student hours, this is like 50 hours for every object, which is not a very scalable solution. right? And so the whole point of RL was to make this scalable. You should be able to drop it into an environment and have it learn. But if we had to do all of this work to instrument the system, to write the reward function, etc., it defeats the point. Okay, so the question is, what do we really care about, right? Do we care about rewards or do we care about what the human wants, right? So what we really want to do is we want to maximize some notion of, human happiness, utility, whatever, right? And so really we want to think of a more data-driven approach to reward supervision. So a human wants to maybe specify some data indicating what task is to be performed. We want a reward inference algorithm that's able to take in this data and some experience from the robot and infer rewards, right? And then you can stick it into RL. So rather than having a human write a program for it, we want to take a more data-driven approach, and that's going to scale better. It's going to learn without the instrumentation. You can learn from vision and so on, right? And so that's what we're going to try and think about in this section. How do we actually go from hand-designed rewards with lots of state estimation and instrumentation to something where we just specify, let's say, images of success, right? So you can just specify images of what successful outcomes look like and have things infer rewards from that. So the setting we're going to think about is that we're just going to provide images of successful milestones. So let's say we have a task like picking up this pipe and inserting it. We're just going to provide some images of what successful outcomes look like, right? And then we want to use that in order to infer rewards for the system directly from images. You don't want to use any instrumentation. If you look at this object versus the previous object, there's no, state estimation. There's no motion capture system anywhere. We want to do all of this directly from vision. And the way we're going to do it is just by training a classifier, right? The stupidest thing you could do. We just want to say, let's collect some images, right, from each of these. We're going to treat them as positives. And then we're going to treat everything that you collect on policy as negatives. And then you're just going to train a classifier, right? What that's going to do is going to reward behavior that's similar to each of these successful outcomes and give zeros to things that are not similar, right? And you can kind of think of this as just like training again, right? So your expert data is your positives. All your on-policy data, things from your policy are negatives. And then you just train a classifier to separate between them. So it's just again, it's something like inverse reinforcement learning. It's you can do this directly from images. You don't need any of the state estimation. It's all coming from data. And this lets you like learn your policy. Okay, so what this scheme overall looks like is you're going to treat your successful examples as positives, all on-policy data as negatives. You're going to train a classifier and use the log likelihood as the reward. It's super simple, no fanciness, just a little bit of regularization. And what that allows you to do is then chain these things together. Let's say you have a three-step task, you just have a classifier for each one, and then you can use this data to figure out how to switch between the classifiers and the reward for each classification step. Right, so you're just going to say, I'm going to provide images for each step, learn 3 classifiers, and then switch between them to solve a multi-step task. Right, and so the point here is that we can get behavior that looks like this. Right, so you get multi-step behavior that looks like, grasping a hook and hooking it in a particular position or inserting a pipe, but you don't need any of the state estimation or the instrumentation for that. You don't need to, hand write a switching mechanism. It's all coming from the same data. And so you've removed a bunch of these like training wheels that you had in the last section. You can use this for more dexterous tasks like brushing, right? So you can try to do things which have more dexterous in-hand stuff. But the important point I want you to take away here is that we've removed the need for this hand-designed task switching. We've removed the motion capture system. We've removed the hand-designed rewards. All we're providing is images of success, right? So in terms of usability, now someone just comes in, provides some images of success. You literally go home, and then you come back the next day. Kind of works, right? The problem is, kind of works is not good enough, because what often happens is the robot breaks or the object breaks or the arena breaks or something falls out. If you leave these systems running for long enough, they will find a way to break everything that can be broken, right? And so the last part of what I'm going to talk about is just a way to kind of reduce the time that this whole system takes. 5 minutes, right? Yeah. And so I'm going to try and think about how we can get these systems to learn a lot quicker, so that we don't have to, wait 70 hours to get any of these skills to be learned. As a result, you're not breaking everything in your environment. Okay, so the last part of what I want to talk about is how do we get systems that are learning on multiple different objects. Let's say you have the object from before, but also a pipe and also a football, right? And as it goes between these different objects, it gets more and more efficient, right? So we want to build systems that get more efficient over time. And the question is, how do we enable this? Right? And what we're going to do is something, frustratingly simple. We're just going to reuse data from previous problems and new problems. So we're not going to transfer any policies, no skills, no nothing. We're just going to take data that is used in the first two objects and use that as initialization for the buffer for the third object, right? So we're going to rely on the basic principles of off-policy, offline reinforcement learning, where we're just going to try and use data as a way to do transfer. So let's say you had, these two objects that you trained before. You have data from the training process of both of these objects, and then you have a new object, and you're learning how to do this, in-hand orientation for this new object. All you're going to do is you're going to combine the data from the previous buffers and the new buffer, and that's going to give you a big boost in learning efficiency, right? So you're just going to say, I want to do off-policy reinforcement learning, standard RL stuff, but you're just going to try and combine data from your previous tasks and your new tasks together, and that's going to let you transfer information across these problems so that you get more and more efficient as you get more and more data, right? And the important part is that data is not random. That data has like good coverage, good exploration, and that allows you to transfer information. Right, so what this would allow you to do is kind of have a pipeline that looks like this. Let's say this is the pipeline for a single object. You do a reset, you do in-hand RL, the object drops, you repeat, right? You can try this for the first object. You can do this for the second object, and then you just transfer the replay buffers to the third object, and that automatically just gives you a big boost in efficiency. And so it's frustratingly simple, which is likely to work. And so you can see that this gives you, pretty big improvements in performance of up to 15 to 20 hours in terms of training time by doing something as simple as transferring the data. And so the whole point here is that as you get more and more objects, the training time gets smaller and smaller and smaller, and the system gets more and more efficient asymptotically. And so the whole point is that we can then train on this new object with around a 15-hour reduction, and that seems like a plus. Right? Okay, so we removed some of these pieces of dirty laundry. We obviously have more, right? So for instance, we're doing this relatively simple set of tasks. The robot tends to break every so often, and so lots of the cool hand design stuff could be useful here. But my point is that the dirty laundry might never end, but we must always strive to remove the dirty laundry and at least be upfront about it in our papers. The higher level point to take away is that I think that RL is less limited by algorithms than it is by systems. And when you think about deploying things into the real world, you can't really cheat, right? So you can't really cheat the assumptions. And so it's useful in terms of designing better algorithms, to know where to focus. It's useful to try and deploy your systems in the real world. And considering the cost of the data, not just the amount, is a useful mechanism. Okay, this is everyone who did the work, not me, but yeah, happy to take questions. Thank you.
Okay, yeah, thanks Abhishek for the inspiring sharing. Okay, we have time for questions. So maybe let me start with one. Okay, so I'm very interested in that work, like you try to learn the reward for the kind of in-hand manipulation. So my question is, especially for these things learned from like successful data demonstrated from human, how generalized would that reward be? And like maybe the question is, how would you make the reward really generalized?
Yeah, that's a great question. I think the nice thing about this particular paradigm is that because it's only requiring positive examples, they don't have to literally come from this system. You could like use a web scale data set to get positive examples, right? And so it's potentially a lot more generalizable because it's just training a classifier, not really like a value function or anything too clever. And so I think using data from other sources would help it generalize better. We don't do that here, but I think that'd be cool.
Great, thank you.
I have a question over here. So speaking about the dirty laundry, we see a lot of works like your work, our work as well, where everything is in this very clean sort of environment, almost like a box.
Right.
So I feel like it's maybe easy to do a lot of things like reset free learning or, multitask learning over there. But what would it take to actually go away from a setup where you have yourself built and created? Yeah, or we, not just you as a... Yeah,
no, I get it. Yeah. That makes sense. That's a great question. I've been thinking about it myself a lot. I don't have a great answer, but I think maybe one mindset change that we need to make is that if we're dropping robots into truly human environments, like your house or your office or something, like I think humans are more helpful than we think. And so, for instance, like here we had to remove the walls. We had to put in the walls because we didn't want it to fall out because no one's going to pick it up. But if you put something in the middle of your living room or your lab, like someone is going to help it. So I wonder if by putting things into human-centric environments, the learning problem can actually become easier. And so I wonder if we just take a leap of faith and put it directly into those environments, will some of the problems we think are problems not be problems? I don't know.
Yeah, thank you for your talk. I had a question about the positive visual examples you were giving kind of in the middle of the talk. Like giving an image that's a good example of what you want is easy, or like it's easy to understand. Do you have an intuition on what makes a good negative example?
Yeah, that's a great question. My sense is that, so I guess the way that this system works is that it treats everything on policy as negatives. So it's like a GAN, it treats anything generated as negative because essentially if you don't, then your policy tends to exploit everything. But that's not a very scalable way of getting negatives, right? Because like it requires you to essentially, it's like whack-a-mole where you have to like whack all the moles, right? But I think if you have reasonable coverage and some amount of smoothing, it tends to like push down a lot of the modes. And so I would say if we get reasonable coverage over the workspace and then do a lot of regularization, that might be a good way to get negatives. Yeah, I haven't tried it, but cool. I think Xingyu had a question.
Okay, we have time for one last question.
Hi, thank you for the talk. You mentioned multiple times that things break during the RL process. I wonder what are your thoughts on ensuring safety during the learning process, especially say if we put the robot in a human environment?
Yeah, that's a great question. I've recently been subscribing to this philosophy of safety by incompetence, which is like if your robot is soft and like useless enough, it's not going to break that many things. I don't think that's the whole story. I think that's part of it. In that if you like have a robot that's like relatively innocuous, like the hand or like the Widow X or something, the amount of damage it can do to the environment is relatively small, but it can keep breaking itself, like I talked about. I think using simulation as a way to ensure safety is pretty sensible, or using human in the loop interventions to provide safety is reasonable. But I think that in conjunction with better hardware design would be a plus.
Okay, yeah, let's thank our speaker again.
Thank you.
Hi, we were going to take a 3 minutes break and be back here at 4:55 for our invited student speakers.
How do you connect? I don't know, HDMI or something?
Oh, maybe you can just
Go on Zoom?
Go on Zoom and
Oh,
share
it's
screen
okay.
and using everything from this computer. So just mute yourself.
What is the link?
Do you have the? Maybe you can get.
I think I saw it on Twitter.
Okay. Yeah.
Yeah, I guess not so many,
Yeah,
but
maybe
that's fine.
next time we will take the posting session this time.
Yeah, I mean, 5% pretty good. Yeah, I mean, I know like some people do like put like the best speaker. Yeah. Best speaker. Stand down, yeah. So it's also pretty tricky. But I should share the screen, right?
Yeah, by the way, also thank you. Yeah, thank you very much.
No problem. Thank you for inviting me. It's no problem. It was pretty easy to prepare that talk. Yeah.
already recorded.
So you're posting it?
Do you want to record it?
Yeah, that's fine.
Yeah. I think only one speaker does not work, so we interrupt the pass
I
and
see.
all other presentation will be recorded. Later will be shared somewhere on the website.
Okay, thanks.
Yeah, still hears like.
Sorry?
I think a lot of people just like the one who will still be here.
Yeah,
So,
they're most
that's
interested.
the
Yeah, yeah. Yeah, I guess people are taking trains already, like tonight.
Yeah.
I know people are going to Seoul. So. I'm ready to start whenever you like.
Hi, okay, guys. So we are beginning our next session. So the invited speakers from UC Berkeley. Yeah, maybe you can, just. So let me introduce the speaker. So the Carmelo is a postdoc from UC Berkeley, working with Professor Peter Bill. His current research interests focus on multimodal sensor fusion for reinforcement learning with applications to dexterous manipulation. He received his PhD at ETH, where he worked on tactile sensor design and sim-to-real learning under the supervision of Professor Ruffalo and Joe. Yeah, I think that's the pronunciation. Okay. For his work on tactile sensing, Carl was a recipient of the 2022 ETH Medal and the Best Paper Award at the 2020 IEEE Internet Conference on Soft Robotics. He was selected as an RSS pioneer last year. The title of this talk is The Power of Sense, Generalizable Manipulation from Vision and Touch through Masked Multimodal Learning. Let's welcome our speaker.
Thanks for the introduction. Okay, let's dive in. Okay, I'm pretty sure everyone has noticed here that tactile sensing is finally flourishing. And obviously, it's not only about optical tactile sensors. We've seen like a lot of different sensor technologies being developed. We just saw test talk before. I was pretty excited to see also you just talk a few days ago about using force sensing resistors sort of to emulate dexterous sense of touch for manipulation. And the interesting thing about this, and that's actually very exciting, is the fact that most of the sensors on this page have been developed during the last 5 years, and that's kind of an impressive development rate. But this is not going to be another sensor design talk. Tessa has already given one, and I'm going to move a little bit forward because actually algorithms are falling behind design. And the reason, again, is this very impressive fast development in the design of tactile sensors. So why are algorithms falling behind design? There are multiple problems, and the first one is that algorithms are sensor specific. So everyone gets their tactile sensors and builds like a method that works for the tactile sensor, but how about transfer across sensors? So this kind of really demands for common representations across sensing principles. This was kind of part of my PhD work at ETH in Zurich. We also developed our own system, tactile sensing design essentially was an optical tactile sensor that provided us with images kind of representative of the deformation of the external membrane. What we came up with was an architecture that could transfer, convert these images into three-dimensional contact force distributions, very general quantities that tell us about everything we want to know about the contact with external objects. However, we have all the other problems that are slowing down algorithms. And that's, for example, the fact that algorithms are also task-specific. For example, the one at the bottom is the classical tactile sensing pipeline that's being used today. We have a tactile sensor gives a raw tactile input, for example, pixels for optical tactile sensors. And then we engineer task-specific features, lower dimensional, for example, contact points. If we look at dexterous manipulation, they can give us good starting point for learning a new policy. However, deep learning is very general, and we actually do not need to hand engineer a task-specific feature. But this opens up a lot of questions on how we actually use tactile sensing inputs in a deep learning context. In addition, tactile sensing is not the only sensing modalities we have for robots. We also have vision. We also have other sensors that are very powerful and often complementary to the information provided by contact sensors. So I'm gonna look at three main questions today when we look at tactile sensors and deep learning together for robot manipulation. First, what are the right architectural choices we wanna make, and what are the right representations we need to reason about as an abstraction for the policy to learn? And additionally, when we have other sensors, what is the right way to fuse touch with the other modalities? And finally, I'm gonna look also at the bonus question, and the question is, if we have perfect visual information, how does touch help? This is a question that has been repeatedly asked in the tactile sensing community over years, and there is very little answers about that so far. Okay, let me introduce the method. We presented masked multimodal learning, or M3L, that efficiently fuses visual and tactile information for reinforcement learning. The method alternates between two phases, the representation learning phase and the policy learning phase. So these are alternating in a loop. So first representation learning, then policy learning, and so on. And when we do representation learning, the policy learning phase is frozen and vice versa. So let's start from the representation learning part. So here we use a masked autoencoder. What is the masked autoencoder is an architecture used for image representation learning, where the original input is masked, and there is a reconstruction loss that tries to indeed to have like an encoder-decoder architecture to reconstruct the original input. Here we do not only have images, but we also have multi-finger tactile force maps. These are again three-dimensional force distribution readings, very general, not specific to any particular sensor. Again, here we have a masking part and a masking architecture, or like we have some masking choices to make, and that's what I'm gonna look at next. So how does masking work? Let's say we have an initial batch of features where V stands for visual features and T stands for tactile features. How could we actually map those, mask those? So obviously there is uniform masking. You just mask tactile and visual patches uniformly and then across modalities. But the issue here is that the encoder-decoder architecture will kind of learn the easy way, that is predicting the masked visual patches from the visible visual patches, and the same for tactile. But we want information to be kind of shared across the modalities. So what has been done with very much success in the vision language community is to mask modality-wise. So what they do is they make sure that at any data sample in the batch, one of the modalities is fully masked, so that there is kind of some forceful flow of information from one modality to the other. This doesn't work well for vision and touch, and the reason is that you can imagine if I grasp any object at a specific location in the space, the touch reading I get is the same that I could get in any other location of the 3D space. So there is kind of a one-to-many correspondence between touch and vision. Well, it's kind of easier to manage to predict kind of touch from any visual input. It's not always the case, it's much easier, there's less ambiguity. So that's why we combine uniform and modality masking to propose asymmetric masking. What asymmetric masking does is that it makes sure that for some of the samples, the touch readings are completely masked out and they are predicted from vision, so that there is some forceful flow of information from vision to touch. But for other samples, what we do is we uniformly mask such that there is still the possibility for the architecture to learn to predict vision from touch too. Okay, going back to the representation learning architecture, the important part here is that we get some latent representations that are shared across vision and touch, and that's what we use as an input to our policy learning phase. So going back to the original scheme and the policy learning, we can extend this to such an architecture where we essentially have latent representation obtained through the representation learning phase. We freeze this latent representation and we use them to train a policy via PPO. Okay, let's look at the task that we have addressed. We looked at a tactile insertion task with different level of randomization in the objects and a door opening task from RoboSuite. Here, the tactile sensors are simulated through the Mujoko touch grid. It's a very recently released touch sensor plugin in Mujoko. It just aggregates the forces in this three-dimensional contact force distribution. We did several ablations. Most importantly, you can see on the bottom left that our approach largely outperforms an end-to-end approach, really leveraging the fact that the reconstruction loss gives us very powerful representations to learn upon. In the middle, you can see the ablation and the masking schemes with asymmetric masking that outperformed both the uniform masking, but also the modality masking that performs quite bad, again, due to the ambiguities present in predicting vision from touch. I promised I would also touch another topic, which is how does touch help in such tasks where actual vision information is sufficient to solve them. We looked at the insertion task, and there we tested on an unseen object. Well, for the door opening task, what we did is to increase the friction coefficient 10 times in the handle. We compared three architectures, which is our architecture that uses both vision and touch to reconstruct the original inputs. And that sequential architecture, which is essentially the same architecture, just that we feed vision and touch separately such that they cannot attend to each other. So the representations are still multimodal, but again, vision cannot attend to touch and touch cannot attend to vision. And finally, we also have a vision-only baseline. If we look at the success rate and the generalization, you can see that our approach consistently outperforms the others. The interesting thing is that it also outperforms the sequential baseline, which is also multimodal, but just doesn't fuse the information the right way. Okay, takeaways from this talk. Tactile sensing hardware has matured a lot in the last 5 years, and I think it's a very exciting time to finally work on algorithms to further advance the field. Tactile sense is complementary to other modalities, so it doesn't have to, we don't need to use that alone just to demonstrate proof of concept. We finally need to merge it together with the available modalities that we already have on robots. Tactile data is high dimensional. This makes learning hard. Therefore, we need to focus on sample efficiency if we want to go towards real-world applications. And finally, multimodal data seems to improve generalization, but this is only true if this multimodal data is fused the right way during training. Okay, with this, I'd like to thank my co-authors. Yongon is actually here, and if you have any other questions, please feel free to ask, and be happy to take them. Thanks.
Thanks for our speakers and a wonderful talk. Yeah.
That's super cool. So I had a question of, is it worse to use touch in certain problems? Like, let's say the touch data is like very noisy or hard to predict, like on some like irregular surfaces or something. Do you see it ever being worse to use that versus just vision, or does your transformer take care of it?
That's a great question. I didn't show them here, but if you look at the training curves in domain, and you compare vision versus vision plus touch, for some of the harder tasks, actually touch doesn't even help. At steady state, yes, of course, but it kind of makes learning more difficult. And the reason is that the representations, take some time to train. Yeah. So I wouldn't say it hurts. It's just it makes things slower. But then if you look at the generalization case, the advantage is kind of consistent. So I would say like it's okay to make a trade-off training time for an advantage generalization time.
Cool, thank you.
Thank you, great talk. I talked to a few people who worked with touch sensors, and especially in the context of sim to real, people tend to binarize it almost always. Do you have insight into that? Is it always a good idea?
Yeah, I definitely believe we need some abstractions. The question is what these abstractions are. Binary is easy and seems to work for certain tasks, but you're throwing away a lot of information. I believe force is a good abstraction, and we had some results in the past where reasoning at the level of the forces first makes simulation easier rather than going all the way to the raw input, but also make transfer much more robust. Yeah.
Makes sense, thank you.
Hey, nice talk again. So I had two questions actually, one on the system side and one on the algorithm side. So you use the Mujoko simulation for the tactile. Now, in your first slide, you showed a variety of tactile sensors, many of which are hard to simulate. So I was wondering if you, from your past experience, do you feel like all of them would work in the same way along with a vision sensor, or do you need special algorithms for each of the different modalities of tactile sensing?
Yeah.
So that's my first question.
Should I answer this first?
Yes.
Sure. That's a great question, and I agree. It's not easy, like, to get to the same representations with different tactile sensors. I think vision-based tactile sensors are very rich in information. So whatever the principle is, I think you can get most what you want from them. There is some work, for example, on the BioTac as well, that looks like a sparse sensor, but the fact that the signals are continuous for each of the taxils allows you to predict a much finer scale at the level of forces again. So I believe most of the sensors are able to capture the information we want, what we have in our fingers, which is force distribution readings. So I believe, yes, most of them have the information there. The question is, like, are the architectures going to be the same? And that's, I think, still an open question.
And then on the algorithm side, when you do this masked reconstruction thing, if you just do random masking and reconstruction, shouldn't you get the same effect, since there would be some random masks which also have the sort of asymmetric masking, right? Would that also give you the same effect, or do you really need to have the asymmetric masking?
Yeah, so the uniform mask is the one in green here. It's better than doing the modality masking that seems to hard performance, but is still below the performance of the asymmetric masking. And I think the reason here is really that some mascot encoders have the issue that although the masking ratio is pretty high, they tend to interpolate. And if you give some visual tokens, they're going to have a lot of influence on the learning process when you predict vision, and the same for the tactile tokens. So by really constraining 50% of the samples to do the asymmetric prediction, then you kind of convince the network to really reason across modalities rather than reasoning modality-wise.
Thank you so much.
Okay, thank you for the great talk and to fusion the sensor, vision, tactile, and all this information to learn Dexterous manipulation.
Thanks.
So maybe last we invite our next speaker, Hao-Shu. So let me give a brief introduction for Hao-Shu. Hao-Shu is currently a fifth-year PhD candidate in Shanghai Jiao Tong University of Department Computer Science and Engineering. He earned his bachelor degree in the same university in 2019. He has been selected as a recipient for several awards, including the CCFCR Rising Scholar Award and Baidu Fellowship, both in 2019. His accommodated work also earned the MSRA Fellowship in 2020 and the BitDance Fellowship in 2021. His research is primarily focused in the field of robotics manipulation. Hao-Shu has an interest in uncovering general structure prior for manipulation through interaction, with the aim of improving the efficiency and robustness of robot learning capability. So let's welcome Hao-Shu for his talk on data efficiency for robot manipulation.
Oh, hi, everyone. Well, okay, good afternoon. And today I will give a talk on the topic of data efficiency in robotic manipulation. And I'm Hao-Shu Wang, so Yuzhe has introduced me a little bit. And one thing I want to mention is that I have several represented projects, that is RH20, UniDexGrasp, and AlphaPost, and I will introduce them later. Well, today, as we all know, that it's almost a consensus that data is the bottleneck in robot learning community, especially for dexterous manipulation. And if we go through some papers, we can see like sentences like haven't converged on appropriate data sets. It's costly to collect data, and the current data set provides a limited number of tasks. So today I want to show some discoveries during my research experience that can help to improve the data efficiency for robotic manipulation. The first is watch out the data scalar dimension. Second is general structure priors can help, and accuracy is more important than low cost in teleoperation. And the last thing is that low cost hardware for data collection. So first, I want to introduce a lesson from robotic grasping. Well, several years ago, data is also a bottleneck for robotic grasping, if we still remember. And if we check paper in 2015 or 2017, you can see like sentences like it's challenging and it's tedious. But today, the state-of-the-art system have achieved human-level performance. So what happens during this process? Well, for data collection in robotic grasping, an intuitive approach is that in the deep learning area, more and more data means better performance. So people just collect more and more objects and usually annotate hundreds or to thousands of grasp poses for each object. However, does larger data set means more objects? What does larger data set mean for the grasping problem? Well, let's look at this picture. If we do not consider the task-specific requirements, the larger data set should provide richer local geometries inside the gripper. But perhaps this does not mean more objects. And we conduct a grasp coverage analysis. We first collect two training data sets. V1 has 40 objects, and V2 has 144 objects. We then take a guard object set as a test set. It contains over 2,000 program-generated objects that complex shape. And let's annotate some grasp poses in the training set. Then for a test object, if we find a similar graspable local geometry in the training set, we say it is a covered geometry. And in the right figure, we show an example of covered local geometries in the testing set. And given training set V1 and V2, we want to investigate how well the graspable local geometry in the training set can be covered or can cover the test object set. And we found that when we uniformly sample 1 million grasp poses on each training set, on each training object, we show the coverage curve as below. And we can see that for V1 and V2, although V2 has about 4 times more object, the coverage curve only increased a little bit. But when we sample 4 million grasp poses on each training object, we show the coverage curve again. And it is obvious that increasing the label density on training set is much more important than increasing the number of training objects, as we can see in the right figure. So here I show some examples that our training set, which contains the colorful object that cover the graspable local geometry on the test set, which is the gray object. We can see that although the object shape may be very different, we always can find some similar local geometries for grasping. And inspired by this observation, we propose GraspNet 1 billion. So in this data set, we provide real-world perception and dense grasp labels at billion level and a standard evaluation platform. So here I briefly go through the data collection and annotation process. First, we just attach 2 cameras to the wrist of a robot, and the robot moves along a fixed trajectory containing 256 calibrated viewpoints. Each viewpoint, the 2 cameras just took images of the scene. And then for each object in the scene, we can densely annotate grasp poses with some analytic model. And after that, we annotate the object-specific pose manually. And the last thing is that we just project the grasp poses to the scene. And it takes less than an hour to annotate a scene. So in this table, I just want to show that we can collect over 1 billion grasp poses, which is orders of magnitude larger than previous data set. And based on this data set, we develop AnyGrasp. So here I would ignore the technical details and just want to show what we can achieve after training on billion level grasp poses. In the left demo, I show a robot that's trying to clean the fragments of a broken plot. We can see that each fragment have a random shape, but the robot can grasp them very good. And in the second demo, I show robot picking over 300 unseen objects, including deformable objects, tiny objects, or like with different shape and materials. And we demonstrate that it's pretty efficient and effective. So AnyGrasp will also provide a closed loop control. Here is a demonstration that I personally I like this demo very much. And you can see that the robot tries to grasp the swimming robot fish in the water. And the camera is mounted on the robot, and we do not track the fish explicitly. All the input to our network is just the depth image of the scene. And Laura, this is also teach a robot to fish, right? Okay, due to the time limit, I will skip the remaining part of this video. And here I show a table comparing our results with previous methods. You can see that, for example, although DexNet or Contact GraspNet, they were trained on over thousands of objects, but they just tested on 50 objects and show a success rate about 95% or 78%. But when we reproduce them in our experiments and we tested them on over 300 objects, you can see that DexNet can only achieve like 76%, while our method can achieve over 90% success rate. And this kind of success rate is comparable to human subjects because we invite some volunteers to conduct grasping with a parallel gripper. And AnyGrasp shows an on-par success rate with human subjects as well as efficiency. And the second thing I want to share is that some general structural priors can help. Well, this is a discovery during a project of dexterous grasping. Well, we know it's very difficult to learning general dexterous grasping because first, there are many different dexterous hands. Second, it's hard to model the contact. Third, it's hard to model the kinematics, especially for some soft hands. The last thing is that it's also time-consuming to label the data set. So we hope to find a method to enable robots to learn dexterous grasping for different hands efficiently. And why is it hard? Well, in previous methods, the researchers usually use a neural network that takes raw observation as input and directly approximate the final grasp success. But mapping from raw observation to grasp success is highly nonlinear, so a lot of data is needed. However, we propose to decouple the representation and decision model, which means that for the first step, we found a general grasp-centric representation, which we call it circular antipodal representation. And we directly learn a mapping from raw observation to this representation. And this step can be trained on our previous GraspNet 1 billion dataset. And for the second step, we just learn a mapping from this intermediate representation to the grasp success. And since only a small number of training data is needed, we can collect data directly in the real world. And this is, in fact, a working submission, so I cannot share too much details, but I can share some results. Well, for a novel gripper, we only train it on 40 objects with only like 500 to 1,500 trial and errors. And during testing, on over 150 unseen objects, we can achieve over 80 to about 87 grasp success rate. The third thing I want to share is that during teleoperation, accuracy is more important than its low cost. Well, we all know that teleoperation is an important approach for collecting robot manipulation data in the real world. So what is important for teleoperation? Well, previous researchers have proposed to collect or use an input device like VR remote or mobile phone. However, it is very inefficient, unsafe for complex and contact-rich tasks. I'll show why it's not a good choice. Well, in the worst case of teleoperation, we can assume that we buy 2 robots and use one of them as the input device. So assume we need 10 seconds to accomplish a task in the scene. Then it takes us 20 robot seconds. So half of the robot time is utilized, and it means that the lower bound of data collection efficiency is 50%. But if we use a VR remote as the input device, if we can finish the task in less than 20 seconds in this case, then it is more efficient than the above case. However, we observe that when using a VR controller as input, it usually takes more than 20 seconds to accomplish contact-rich tasks. So it means that it is not a good choice to use a VR remote. So in order to solve this problem, we just propose an efficient data collection platform to collect data. We use a haptic device, and in the right side, I show it is also a demo that I quite like. Well, we can see that the robot can cut vegetables, which is a very contact-rich task. And this video is not accelerated. So we can see that it's very efficient to collect data with a haptic device. And based on this data collection platform, we present H20. It contains over 140 skills, 100,000 contact-rich robot manipulation sequences. And each sequence contains visual, force, audio, action information, and a corresponding human demonstration. So here is a data example. For each task, we provide human demonstration as well as multi-view robot manipulation. The human demonstration is also multi-viewed. And we found that set up multiple cameras can also improve the data collection efficiency. And in our data set, all the cameras are carefully calibrated with robot base. So are the force torque sensors. So we can have a coherent action space in the image coordinate during training. And this data set is also open sourced. So the last thing is that low-cost hardware is important for data collection. Because as mentioned, if in the worst case, we buy 2 robots that are the same, the lower bound of data collection efficiency is 50%. But if we replace the input device as a cheaper robot arm, the lower bound of data collection can improve. And Aloha is a very good choice, but it's still not cheap enough. And we are currently building low-cost hardware to support large-scale data collection in the wild, and it's still an ongoing project. Hopefully, we can present it in September. Oh, thanks a lot for your hearing, and I'm happy to take any question. Thank you.
All right, thank you so much for the talk. We are running a little low on time because we have to close by 5:30, so I have time for one question. So if you guys want to ask a question, please feel free. Oh, wow. Okay. Yes, Laurel.
So I have a question about the RH20i.
Yeah.
Have you trained any models from it, and do you see any improvements with larger amounts of data? So it's a lot of data, it's really cool, but I'm sort of curious about, is that large amount of data actually useful?
Yeah. We tried to train a RT1 baseline, but we found that it does not work quite well. And a reason is that we move our lab during this process. So the viewpoint of the camera. We don't have the same viewpoint of the camera. And if you check out previous paper, all the viewpoint of imitation learning is always fixed. So we are trying to add some 3D information. And we found that combining RT1 with diffusion policy indeed improves the performance, but still it's not promising. And we are currently integrating 3D information into this pipeline of the model into the model training. Yeah, thanks.
Very nice work. Thanks.
Thanks.
All right, thanks so much. Let's applaud once again for our speaker.
Thank you.
All right, so we're almost at the end of our session. Thank you so much for attending. Let me just share my screen so that we can close out our session. So presentation, slideshow mode. All right, so this is the closing remarks. We are at the end of our session. Thank you so much for attending our first workshop on learning dexterous manipulation at RSS 2023. And everyone who joined in via Zoom as well, we appreciate your participation. Let's just thank a few people. So first of all, we want to thank our speakers. Thank you for taking time out of your day to be here and just speak at our workshop. All the talks have been really amazing, and I think we all learned a lot. So let's just give a round of applause for our speakers. Next, I want to say thank you to all the people who helped us organize. And of course, all of them worked really hard to get it going. And hopefully we can have more of these workshops in the future. So again, thank you all for organizing this. So another round of applause, really short. And once again, we couldn't have had this here if RSS wasn't happening, and RSS was quite the large organization hassle, as you could all see, and we are at the end of it. So thank you for the RSS organizers. Round of applause. And finally, I would like to thank the people who are here. Thanks to you for being here. Thank you for attending the workshop. Thank you for making it a success. I really, really appreciate your participation, and I'm sure my co-organizers also feel the same way. So round of applause for yourself. And with that, we're gonna close out our workshop. Thank you so much. The recording would be made available on the website, but thank you so much for being here. The workshop is closed now.